Good day and welcome back to the X.Org Developers Conference 2021. It is the final Thursday and we'll start right off the bat with the opening session by Radek Schwichtenberg. Radek, the stage is yours.
Welcome on the last day of the XDC 2021 conference. We again have a quite busy lineup for today, full of great presentations. So I will not be keeping you waiting and jumping directly to our logistics for today. Before that, let's give a round of applause to all our sponsors. Thanks a lot for our platinum sponsor this year, Intel Corporation. Thanks a lot to all our gold sponsors, Google, NVIDIA, ARM, Microsoft, and AMD. Thanks a lot. Thank you to silver sponsors, Igalia, the Linux Foundation, and Collabora. And big thank you also goes to bronze sponsors this year, GitLab and Kronos Group. I would like also to, say big thank you to our supporter, C3 Vogue this year for providing us great streaming experience for our viewers. The conference is being brought to you this year by Intel, working with X.Org Foundation. Thanks a lot for letting us, as I represent Intel, letting us, provide this experience second time in a row for X.Org community and graphics community in open source. Thanks for that. Useful information is all available on our website. Links are shared on IRC, on Twitter. If you have any questions, reach out to us directly on IRC. We still have our hallway discussions GC instance for anyone to use. Make sure that you create rooms, you share those with other people attending the conference, and that you share your discussions or summaries of them in the lightning talks at the end of the day. The program is available on our website. There were small changes in the program when it comes to the workshops, so make sure you check it out. And while we are at the program topic, today, while reviewing it, I just realized that the name of one of our speakers changed. And sorry for bringing it up, but I'd like to congratulate an X.Org member, one of the XDC organizers last year and many years in the past as well, Martin Roukala. I hope I pronounced it correctly, previously known as Martin Perez, on getting married. So I'm really happy for you, Martin. Wishing you and your wife all the best. Getting back to the rest of the logistics now. Lightning talks, it's last day of the conference, so if you have something to share, please share it today in the afternoon session. Deadline for submission of lightning talks is 15 minutes before they start. So it's 5 p.m. 35 UTC +2. There is workshop that was added to the to our day today. It's starting in a couple of minutes, so please check out the website and make sure that if you're interested in participating in the discussion, that's your chance. Speakers, make sure you upload your presentation. So far, we have a great track of record here. Thanks a lot. Keep up the good work. In the X.Org Foundation, the organizing team, we all are dedicated to provide a harassment-free conference experience to everyone. So we do not tolerate harassment. And if you see any breaches of our code of conduct that in full can be viewed on our website, please make sure you reach out to one of the following listed on the slide people. You can reach out to the organizers directly on IRC as well. That's it for now. Have a great last day of the conference. Thanks again to all our sponsors, and see you around.
Once again, welcome back to XDC 2021. Coming up after the break is the first workshop of the day, Hostile Multi-Tenancy on a Single Commodity GPU. Can it be secure? Led by Demi Obanur. Have you ever wanted to play games on your computer without having to trust them? Come join us and discuss ideas for a modern, secure GPU driver. Link to the workshop's GC is on IRC. In parallel to the workshop, there are 3 talks, starting with Maxime Repart's Improving the Linux Display Stack Reliability. See you in a few minutes. And one more reminder for people interested in the BVH building session. The first session starts in about 10 minutes, and a link to the GC session is also on IRC. And we're ready to go with the first talk of the day. Maxime Ripart is going to present us a talk on improving the Linux display stack reliability. Please welcome Maxime.
Hi everyone, my name is Maxime Ripart. I'm one of the co-maintainer of the DRM MISC tree, which for those of you that are not particularly involved in the Linux side of things, is the Git tree that is taking care and merging all the patches for all the small drivers that don't have a lot of developers involved. So drivers like the one for embedded SoCs and so on. And today, I'd like to discuss with you some issues I find in the DRM MISC tree in general. Hopefully, suggest a workaround and to hopefully tackle this particular issue and work to getting towards a more reliable display stack on those drivers. So the first thing we need to acknowledge is that KMS basically succeeded thanks to the massive effort to make DRM KMS easier that started like a decade ago. We now have like 60 KMS drivers in tree and getting 1 or 2 new drivers each release, which is great. The amount of development per release of Linux is around a bit less than 2000, which is huge. It's basically a sixth of the whole of Linux development efforts every release. And both of these things, so the fact that KMS is now much easier than it used to be, and that there is a huge amount of development, made FBdev, which was a former display API in Linux, pretty much irrelevant these days. As far as I know, there's no longer any development involved. It's basically just a low maintenance effort fixing like huge issues, and that's pretty much it. The only thing that remains from FBdev nowadays is user space API, and mostly because of the frame buffer console. But we have more and more user space components that are moving towards KMS and abandoning FBdev. And hopefully at some point we'll be able to remove FBcon entirely and get rid of FBdev. So it became the standard these days with all the drivers and display related features that are only targeting KMS. And on the maintenance front, part of the effort that I mentioned above was to actually create a lot of helpers to be able to share most code between drivers, which means that nowadays it works so well that a very simple device can have a driver of about 400 to 500 lines of code, which is like really compact. And so the use of helpers everywhere with together with the so we only have the actually device specific components in the drivers, and those components are supposed to be written in hooks with a clear set of semantics, very well documented. So we know what expectations we have from the drivers, and so it makes it pretty easy to maintain given its size. However, part of the success is that there's a lot of features and a lot of use cases that have been implemented by the core. And so while it definitely works, I guess, for big drivers that have dedicated teams, in DRM MISC, what we see is that we mostly have part-time developers that don't really have the time to invest in getting to know how each feature works, how each feature is supposed to be used, to know each use cases. And so it's fairly easy to overlook or underestimate some of those use cases or features. To downright misunderstand them or misunderstand their requirements or side effects or yeah, basically the impact and implication that using that feature could have on your driver. And it can even be difficult to test them easily because some advanced features might not be exposed by the user space or by the user space that is running on your platform. For example, if some feature is only usable by, say, Android, and you don't have an Android port on your platform, then you obviously won't port the entirety of Android just to be able to test that feature on your device. So yeah, it's fairly difficult for part-time developers to get exactly what are the expectations from the driver. And if we're looking at this graph, it's basically a graph where in X you have all the KMS drivers that we have in 5.14, sorry. And in the y-axis, the number of contributors that have, on average, submitted more than one patch every release since the introduction of the driver in Linux. And so we see that basically all the desktop grade drivers are having a lot of contributors that are active. So drivers like AMD's, Intel, Nouveau, a few embedded grade drivers have that as well. So like Exynos and MSM for Qualcomm SoCs, and Exynos being for Samsung's. And then you have the long trail of basically all the other devices and all the other drivers that have one or two at best developers being active. And well, one patch every release is a fairly low bar still. And so we clearly see that on those drivers, we don't really have like a full time team. Basically, it's usually a couple of developers working on it on the side, aside from other things. I can only imagine that, for example, for all the ARM SoC devices, they basically maintain the entire platform, and KMS driver being one of the drivers that they have to take into account and maintain, but they don't have to, they basically can't and won't invest full time into that driver. And so getting the knowledge of the core of basically what I was saying before is basically a showstopper for them. And so it's going to introduce a few issues purely because of lack of knowledge, and on those drivers, lack of review as well by someone that knows, basically. And it's even worse when you take into account that the hardware is barely accessible to other developers. So the controllers themselves might not be easy to access. They might be proprietary, confidential, not produced anymore, not produced yet. So it might not be easy to get access to one of those controllers or GPUs. And even if you do get one of them and one platform using them, they might not expose all the hardware features that the drivers can implement. And so you won't be able to test everything, basically. So we end up in a situation where we have kind of two groups. We have the people with hardware that don't have the knowledge of the framework in depth and don't really know what to test, basically. And people with the in-depth knowledge of the framework and would be able to know what to test, how to test, and make proper review, don't have access to the hardware and don't have the time to care for all those drivers anyway. So it's kind of an issue, really. And so it leads to some situations like this one that is still currently happening, unfortunately, on the Raspberry Pi. So it initially started with the introduction of HDMI stream link support, which is required for HDMI modes above 4K and 60 Hz, including 4K and 60 Hz. And so this is basically a change in the transmission mode of the HDMI link. And so you would have to notify the display, basically, that you have changed that transmission mode so that both the emitter and receiver can agree on it and the display actually display the frame. Otherwise, the monitor won't sync and you would get nothing on the display. Unfortunately, with this, or fortunately, I mean, it makes sense. When you disconnect the display after it's been set up using the scrambler and then reconnect it, obviously it will have lost its scrambler status. So you also have to determine if and when the display is connected and removed from the system. And so we basically have two ways of dealing with this in KMS. The first one is polling, where basically the core will poll every 10 seconds, if I remember right, to see if, well, to poll the driver basically to have the connection status with the display, and if something changed, then it will report it. But obviously, 10 seconds is quite a lot, so disconnecting and reconnecting it might be an issue if you do it fast enough, or if you have something on the other end that toggles the hot plug line fast enough. And then you have support for interrupt-based hot plug detection, which is better since you can react to all of those events. But not all drivers or platforms are supporting it. And it's basically what was happening for the Raspberry Pi 4. Not all Raspberry Pis were able to rely on interrupts, and there were some issues with some of them on the GPIO that provided the HPD signal. And so you wouldn't be able to use interrupt on those. So basically, the driver was supporting polling only. But since only the Raspberry Pi 4 had the support for the HDMI scrambler, and it had as well the interrupts, support for hot plug detection, the second request I did was to enable those interrupts and be able to report the hot plug based on interrupts properly. As soon as I did that, however, someone came along and basically whenever his TV was shut down, I think, we had a CPU crash and the system would completely stall silently. And it turns out that now that we were able to detect those hot plug pulses, that the user space application that user was using actually would disable the display output when the display was reported as disconnected, which makes sense, right? And would then still try to do an HDMI CSC access on that connector, which since the output was disabled, the controller was powered down, and powered down controller on the Raspberry Pi 4, if you happen to do a register read or write on one of those controllers, you basically stole the whole bus, which was explaining the system stall and silent. So yeah, we fixed that, fortunately. But then we would get another bug report where if you were running your TV in 4K, and then you would put it in standby, turn it on again, then the display would stay black. And it turns out that if you basically what that TV was doing at the moment was that it was creating an HPD pulse to basically fake that the display was disconnected and reconnected. the kernel was detecting it properly, but since it was exactly the same modes exposed by the TV before, and that mode was completely fine with whatever was running on it, we never had a new mode set occurring, and so nothing ever sent to the display the notification that it was supposed to enable the scrambling as well. And so we would have an emitter transmitting with the scramble enabled, and the display receiving without it, which was explaining the black screen. And so it turns out that the proper way to do this is basically when in the detect hook that the driver provides to the system, we were actually, if the display was reconnected and no mode has changed, we would notify the display again, and so everything works. Except it didn't, because we had exactly the same issue coming up with Kodi, and it turns out that, so in our interrupt handler, basically we would notify the KMS core, and the KMS core would call back into our detect hook, and that detect hook would provide to the core the connection status. But that notification to the core and then the call back to the hook was done through a helper, and we used the wrong one. We used the wrong one, and we used one that would just send to the user space the kernel event that something had changed on that device, but we never actually called the detect hook in our driver. And this was working for some application on the bug before, because those applications did have support to listen to those kernel events from the user space. And so the first thing they did when the hotplug event was coming in was to actually query the driver to know the display status, and thus calling the detect hook that we had implemented. But Kodi doesn't support all of this. So Kodi never actually called into detect either. And so we ended up never calling detect. So here the obvious fix was to switch to another helper that was actually calling detect and reporting it properly. And everything was fine until someone came along saying that since that patch, whenever they would wake up the TV using CEC, they would basically end up into what looks like a deadlock for some reason, and I still don't really know why at the moment, because it came up just last week and I haven't had time to investigate it yet. But yeah, my point here being that basically you have a lot of from the framework and drivers, you have quite a lot of expectation. Not all of them are very well documented. For example, the fact that you could do a CEC access while the HDMI controller was disabled was documented pretty much nowhere. So part of that fix was to add that documentation. The fact that you had to restore the scrambler status in the detect in the fourth item wasn't documented, I think. On the fifth item, the documentation was misleading, and I misunderstood it. So we have kind of all those issues coming at once, which just kind of proves my point, I guess. And it's hard for everyone to know all of them. And without knowing all of them, we are kind of have to like uncover one bug after another, which is kind of frustrating and not very efficient. So we could just use CI, right? Especially all those issues are basically fairly standard behavior that could basically happen with any device that can do HDMI, CC, and 4K, which is fairly common these days. And So we should be able to test them, and they should be reported by some kind of CI. And we basically have almost two options. The first one is GitLab, which could be very useful to do so. It's being discussed. Mesa moved to it, but the kernel didn't yet. So it could be useful, but it's not a thing yet. One of the issues when it's going to be a thing is also how do you like get that branch that you just try to merge into tested into a device, which Martin is probably going to have some ideas about later this afternoon, sorry. But you still have to deal with that. And then you have kernel CI, which is fairly useful these days. They have a lot of boards, a lot of access to a lot of hardwares, a lot of tests, but they don't have any display tests, which we could provide, I guess. But then come the questions of which tools should we run? And the obvious first candidate is IGT, which, as you probably all know, is an extensive test suite which has tests for both display and rendering drivers. And for both generic and vendor-specific features, it's great. It's even greater since nowadays, with this new policy, you have to have, for every new feature that you want to provide in KMS, you have to have a matching IGT test. So it only expands its reach, and it's a good thing. There's approximately 2,000 tests. It's well maintained. With this policy, it basically tests and documents pretty much everything. So it's, yeah, awesome. Except that it fails a bit on some devices that are in the RAMMISC, and we're going to see a bit about the shortcomings. The first big one is how you get IGT onto those devices. There's a fairly big number of dependencies, and a fairly big one, like Kero is in there, which, in order to compile it, pretty much requires that you use like some kind of real distributions, so things like Debian, Fedora, which probably doesn't work on some of those devices. The cross-compilation, since you have so many of those dependencies, is basically a non-starter. There's too many of them. You would need to have some kind of custom toolchain. It's very hard. And Docker helps, but marginally. You can't always have either Docker or Podman on those platforms, again, because of size requirements. And still, a build of IGT with the Debian minimal Docker file takes around 700 megabytes, which is, depending on what your use cases are, can be not a lot or way too much. And if we are looking at what a typical embedded device is, and basically what's the lowest common device on those DRM drivers, it's basically not that great. You would expect one CPU, basically 64 megabytes of RAM or more if you're lucky. A GPU from time to time, around 128 megabytes of flash storage, which is going to be probably some slow NAND that doesn't handle a lot of writes. So you can't just put a Debian in there. You can't compile in there because it will just kill your flash. And you have a weak CPU and don't have a lot of RAM. You have no network, and you probably will have more internal display interfaces like DSI or LVDS rather than external ones like HDMI or DisplayPort. So there's kind of a cultural clash in here, and we can see that IGT really doesn't work on those devices. The next thing is that IGT supports test suites because there's a huge number of tests, and so in order to be able to run a given number of tests in a reproducible way, test suites are great for that. There's basically 2 or 3 users, depending on how you're counting, which are Intel and Raspberry Pi. And it's great, but Intel is using a lot of them. Raspberry Pi is basically using test suites only for the Raspberry Pi specific API, so basically the GPU. And if you're not really knowledgeable about IGT, it's fairly hard to see which tests you want to run on a given platform. And given that some of them are like really slow, you can't run all of them either. So it's, yeah, kind of hard. There's a lot of ramp-up time to be able to like get to a state where you have sufficient enough test suites. And it's even harder considering that there's no test suite that any driver must pass. So ideally, we should be able to have a test that says, okay, if you want to have a KMS driver, this is a minimal test suite that basically any driver must validate, and we don't have that. And then you have more like features that are missing a bit from IGT, but are not really missing. It's more of because of the entire design. It's mostly test for the user space API and the driver behavior. For example, in some situations where, like I said, we wouldn't have enabled the AGMI scrambler, basically the driver is completely happy about it. The user space API is going to work fine. The driver will be working fine as well. The controller won't report any error. Everything is doing great, except you don't have anything on your display and the display got broken. So there's a few tools and components that we can use in order to remove that a bit. The first one is VKMS, which is a virtual KMS driver in tree. And VKMS can actually look at the output of the KMS because it's entirely virtual. But since it's an entirely separate driver, it doesn't really test the drivers themselves, but more the core in depth, which is great already. But yeah, we never test the actual drivers. And then you have another feature of DRM, which is write back, which is kind of useful for this as well. It's basically you would take the output right before it goes to the display interface and put back the content into a buffer. So it allows you to capture into memory what would be the output that gets on that display interface, except most of the time it's going to be at the end of the CRC. So it won't be able to test, back to my example, we wouldn't have been able to test the HDMI controller driver, and so we wouldn't be able to like detect that it was completely broken using a write back. So it's still better than nothing, but it's not complete. So it's really more of a test to see if the driver can detect an error and reports it, and if it behaves properly, and not really if the result is, and by result I mean what is actually displayed on the monitor or panel or whatever, is actually valid. There's some kind of device that could help with this too, which is called the Chameleon, which is made by Google. And it basically fake a display and will be able, through an FPGA, to retrieve the frame, compute their CRCs, and then allow someone to pull them from the network. So IGT has support for this, and we'll run a few tests on the device under test, get back the frame, compare what has been sent, what has been received, and see if it matches. However, the Chameleon has several fairly big drawbacks. The three main ones being that it's fairly expensive and very difficult to source. You basically have to ask Google every time. And I'm not sure they would be able to provide something like 20 or 30 of them if you ask them. And then it has a limited number of inputs. It's just HDMI, DisplayPort, and VGA, which is great, again, but it doesn't allow you to test MyPy DSI, LVDS, RGB, those kind of connections. It requires a network connection between the device under test and the Chameleon, which we don't always have. And it's fairly difficult to extend since it's VHDL. And so since it's difficult to extend, we can't have a lot of tests in there either. So it's definitely much better, again, but still far from perfect. And so we end up with a few blind spots with IGT, which is that it's difficult to set up for part-time developers. It's downright impossible to deploy on some platforms or devices. And it might not be even able to tell that the hardware doesn't output anything, and so that the output is completely broken. So like I said, with scramblers, you have the same issue, for example, with a parallel bus, where you basically just send data over that bus and you have no way to tell. The panel doesn't give you back anything. So if you misconfigure the timings or polarities, for example, or stuff like that, you have no way to tell that something is broken using IGT. And so if we had some kind of ideal world, or at least in my ideal world, we'd basically need a tool that has a few requirements. The first one is that it can be deployed easily on any platform supported by KMS. So it's basically ARM, MIPS, and x86. With an overall size of several tens of megabytes, something like that. So something still reasonable, but where you could still pack a few features. It could run without network, and it can be cross-compiled easily. That's for the deployment side, but ideally it wouldn't have any ramp-up time or internal knowledge needed for the tool itself. So you would basically just run it and it would give you whether it succeeds or not. And it can test the driver output optionally with quite cheap hardware and easy to source. So I worked on something like this for the last year or so. And so I'm going to suggest a solution. The main plan is that we definitely have to keep IGT. It's a full test suite, it's comprehensive. The policy to add every test to IGT is great, we definitely need to keep it. We just need a tool in addition to it that can be easy to deploy on any platform of any architecture using KMS. So it would be useful on that lame embedded device and could be deployed on that lame embedded device and would work okay. Where all the KMS drivers are expected to pass all the tests. So something like what V4L2 has been doing for using V4L2 compliance and CEC compliance. So they have those tools that will basically exert the user space API, pass all the tests, and it's a requirement when you actually submit a driver there that those tests are passing before even merging it. It's something that would be valuable for us. Where we could, like I said, using $100 device, test the display output without network, because not all the devices are using it, and can test internal interfaces, so like LVDS, RGB, MyPy DSI, and so on. So the architecture I've been working on has basically three components. So two software ones and hardware ones. So the first one is the tool that we run on the device under test that would optionally connect and interact with an hardware board that is there to capture the dot output. And finally, a tool that would run on that board that captures and processes the frames to make sure that they are proper. So the tool that is running on the dot is, it's basically where we have our strict deployment requirements. And I've been working on a REST application because Rust here is very valuable. Because Rust can be statically compiled without any dependency. The only dependency that is the C library, and it can work with several of them. So for example, if that platform has Muscle instead of the GDC, it works. It can be cross-compiled very easily. It's basically just a flag on the Rust compiler, and that's it. And it can be deployed by just copying that device, that binary to the device, and it just works. So part of that effort was to come up with a KMS library as well, which I did with, and so this application is an atomic KMS application. And in the end, it would be the one that runs all the local tests on the device. And so at the moment, what it does is just test the output part. So it will decode a PNG frame, put it into a frame buffer, output it, and just waits there. So this takes 4 megabytes with the default flags. So we are definitely having something quite compact here. And it's also one of the Rust advantages there, since it doesn't require any kind of runtime or interpreter or anything. Yeah. And then we have the prototype itself, so the board, which is based on MyPy CSI bridge. So the first prototype I did was to test HDMI, but you can find MyPy DSI bridges for pretty much any of the interfaces I've mentioned before, except maybe MyPy DSI. I haven't been able to find any for some reason. And the good thing about it is that you can find very easily, even like if you just want to buy one of those bridges from Cornell, of those bridges. And MyPy CSI capture is also fairly widespread among platforms these days. Basically, any cheap embedded SoC from ARM will have MyPy CSI at some point, so it's fairly easy to source. And so the prototypes I did were based on a Raspberry Pi and an HDMI to MyPy CSI bridge, and it's been working great so far. And so on the capture side, I've used Rust as well, and it's a Rust v4L2 application. It runs basically a configurable test scenario where it will first set up the bridge, set up the EDIDs in that bridge, so generate and program them into the bridge, start the capture interface, and then wait for frame to arrive. Once the frames arrived, it will process them and make sure that they are valid and until that test scenario is done. And so the frame validation is, I'm sure, going to be controversial because it's fairly subjective. But the way I did it was that every frame sent by the dot is going to contain a header. This header will contain a counter and a hash. And so the validation is basically making sure the hash is correct and that the frames are in order, so we never see a decreasing counter. And so part of what I was skeptical about at first was that I wasn't sure we would be able to run a hash fast enough on those frames to keep up at 60 Hertz. And it turns out that on a Raspberry Pi 4, it takes about 5 milliseconds to process a 1080p frame, so well within the 15 to 60 milliseconds of budget we have. The Raspberry Pi 3 is lower at around 8-ish, but it still fits, which means that with some effort, we could probably go to 4K at 60 Hertz. But yeah, that would be a bit tight, or would require something more powerful. And so there's definitely some limitation at the moment of this. So it relies on, so when it's set up, the new EDIDs, the bridge will toggle the hot plug line for 100 milliseconds. And so it basically relies on interrupt-based hot plug detection to be able to switch resolutions. And so it won't work with devices that rely on polling from the core, which is bad. And probably something that we will need to address at some point. The validation based on a hash is rather fragile, and we won't be able to test some of the features like color space conversions, because those would, we basically have the assumption that the frame is left untouched between the time where our application gives it as a frame buffer to DRM and KMS, and then we retrieve it through V4L2. So having color space conversion there doesn't work. Things like having a misconfigured, for example, full range versus limited range RGB will not work either, things like this. But it would still allow us to have some kind of validation, even though it's not as wide as we'd like it to be. We don't really have a way to send parameters from the capture side to the DUTs. For example, expressing something like, we want you to output for 10 seconds and then shut down for 5 seconds and then resume. But it could probably be encoded in the EDID somehow. And finally, the MyPy CH-side bridges and capture devices for 4K are quite rare. So for now, we'll have to limit ourselves to 180p, which is a good first step, but we probably need to go to 4K at some point. And if we want to work on the additional features, we definitely work into integrating it into a CI environment, testing more things, adding support for local tests, testing audio and CEC support, testing 4K, and possibly testing the info frames as well. So yeah. So I asked for if you have any questions on that slide, but I'm actually also a lot interested in having your feedback. It's something that I would be really interested to. Do you see any like fatal flaw in this? Are you interested? Do you completely reject it? Yeah, so just let me know. Thanks. Hi, everyone.
Hey, thank you very much for excellent talk. That was Improving the Linux Display Stack Reliability by Maxim Repart, who is here for the QA session now. Simon says, Sarah asks, how difficult it would be to pump out the frames? Are there Raspberry Pi limitations? Are there RPI limitations that would prevent it?
Sorry. So pumping up the frames actually fairly easy. We just get a V4L2 buffer. So for now, I'm just accessing it to take the hash, but it would be easy to just like send it over the network, for example, and kind of emulate what the Chameleon has been doing, for example. So yeah, accessing the actual frames is fairly easy. It's not implemented at the moment, but it would be easy to do.
Okay, and one more question from Simon Sarah. Are any plans to just adapt IGT instead with build flags, etc.? I think it's a bit unfortunate to end up with fragmented test suits.
Yeah, I kind of agree with the feeling, but it just felt like a really daunting task. So, for example, just getting it to cross-compile easily and be able to be embedded in a fairly simple system was like, well, at least a bit too much for me. And then we could definitely have in AGT, for example, must-pass list, like we discussed and Daniel suggested as well. So I guess it's really just whether it's worth it or not, and it didn't really feel like it for me. But maybe others will disagree with me on this. Yeah.
Okay, it looks like that's it for the questions. So thank you very much for the talk and have a great rest of the conference.
Thanks. Have a nice afternoon or morning.
And we're ready to go with the next talk of the day. Roman Gilg is going to present KWNFTs with WL Roots backend. Roman, the stage is yours.
Yes, thank you. Welcome everybody to the third day and of XDC. And yesterday in the talk about KWNFT, I already teasered that today I'm going to talk a little bit more about KWNFT's new WL Roots backend. And yeah, I just want to give you a little bit an overview, a rundown of how this was implemented, and also a little bit of primer to what WL Roots actually is. And yeah, let's start with this, right? So what is WL Roots? Probably a lot of people listening here already know it, but just to pretty quickly give you an overview, it's a C library you can build Wayland compositors with, and it's used by several projects, like independent also of WL Roots itself. Sway, which is the one not independent, right? It was basically the one which WL Roots was created for. It's a tiling window manager, whereas, for example, also GameScope, a project by Valve to run Steam games with in a very efficient manner. Fog, for example, is I think it's pronounced like this. Fog is by Purism, a compositor meant for mobile phones for their DRM5 and so on. So it's also using WL Roots internally, what maybe not everybody knows. And now there's KWNFT making use of it. So it's actually used by quite a lot of projects nowadays, and it's being actively developed, and there are also regular releases to it, so very well maintained. It's being developed here on the right. You can see it's on GitHub, right, with what you expect from a bigger open source project. So that's quickly to what is WL Roots. The other question is, why did we decide in KWNFT to make use of it, right? So for us as a C++ project, of course, it's because WL Roots is a C library, that means easy integration, right? So it's pretty quickly to work with it, right? As long as you remember to see extern the includes. Yeah, it has a Mason build system. We in KWNFT use CMake, right? Which is, I would say, very similar in many features. Maybe has a little bit more complex syntax as Mason, but it's still working well. And it has good integration also with Mason, or rather Mason features through the package build, a good integration with CMake. So that's also working, yeah, super fluidly. And what's great about WL Roots is a toolkit approach, right? So I will come to that more later. Basically means that you can pick different components and modules of WL Roots without having to restructure all your own code and having to include everything else which WL Roots includes. So you can very specifically pick things out of WL Roots which offer you a lot of simplification of your own code, but still allows you to enhance it with your own stuff. Yeah, and the contributors of WL Roots are just nice to work with, and they are also active in upstream development, freedesktop.org, and so on. And that's very important for me as well. Yeah, if you are more interested in the reasons why KWNFT choose WL Roots, and also a comparison with alternative projects, then I can recommend to you the blog post I did about it a few months ago. So just go to my webpage, and then you can find it at the very top. So quick introduction to WL Roots. Why did we choose WL Roots? I want to give you also a little bit an insight into how WL Roots is actually built up. So if you want to create your next compositor with it, then you already have like a starting point there to begin with. So on a very high level, WL Roots is basically split up into a backend and a front-end part. I call it this way, backend and front-end. And the backend allows to communicate with the underlying platform, or often just the hardware, right, via DRM, talking to the kernel and so on. The front-end on the other side that provides functions, types, and so on, so you can talk as a Wayland server Wayland clients via the Wayland protocol. So it provides a lot of types for that, like for which encapsulate then the functionality of the objects in the Wayland protocol, like WLC, for example. In between front end and back end, but also independent, right, in this toolkit approach is a renderer of WL roots, and it features a OpenGLS renderer, which then talks via EGL to the hardware, and a Pixman renderer for software rendering. There are also other independent components which I will mention here because they can be important for you depending on your needs. There is a session component which provides your functionality to talk to lognd, for example, to get the DRM master and to get the input devices from libinput. And nowadays, it has a CD backend. So it uses CD, which is again another independent project to talk to this session component to the session backend. And that's great because other projects like Western are using it too, if I recall correctly. So that's something where already some streamlining and some unifying happens. So session component is one thing, and then it gives you some other helper tools at hand. For example, the Xcursor library, which basically wraps Xcursor, the library, to get a cursor pixmap. It's kind of an implementation detail of Wayland. And XWM and XWayland server components, which allow you to start an XWayland server and independently of that run as the XWM, which is the X window manager. So if you have the XWayland clients running, then to manage them, the Wayland server must act as an XWM as well. So in a graphical view, that could look like this, right? So you have the front and back end in the middle. These parts allow you on the front to talk to all the Wayland clients, and on the back to talk to your platform, right? And in the back end, you have different plugins, or I mean, they are statically compiled, but you still at runtime, it decides what is necessary. So there you can then either, if you run on DRM directly, right from the virtual terminal, for example, then the DRM backend is chosen, and you usually have another backend put to that, the libinput backend, to talk the input things, right, with libinput. And if you run, for example, your compositor in another Wayland session, then there would be a Wayland nested plugin chosen. And so, yeah, depending on that, your platform, it does that all for you. And the renderer, the session, as said, are independent modules you can use, or the session is actually necessary, right, for the backend in some cases to get the input devices and the DRM master and so on. And there are these helpers which allow you to also simplify your code, which are also independent. And yeah, as said, this toolkit approach is very, 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 very nice to use as a consumer. It's very helpful to not have to use everything, but that you can really pick. And there are also examples for that, right? So going from the backend and front end split, there is now an example of a compositor which only uses the backend part of WL roots as QuinnFT, right? We only use the backend at the moment. We don't use the front end. We don't use the renderer, anything else. Coming to it later, I would like to expand on this integration with WL roots, making use of more components, right? But for now, we only use the backend, and we can do that, right, with WL roots. And there's also an example of a compositor which only uses the front end in comparison, right, but not the backend code, because it has its own backend code. GameScope, you see it there. It's GameScope only uses the front end of WL roots to communicate with Wayland clients, but it doesn't use the backend code because it has its own backend where it talks, where it renders via Vulkan, and has some optimization to use the compute pipeline for compositing and so on. So it's pretty interesting what it does, right? But because it wanted to quickly get up and running this, inside of GameScope, it only chose to use the front-end part. Then there are, of course, examples of compositors which use both, right? For example, Sway and Wayfire are two such examples. Yeah, you can see here some pictures in the top right corner. That's Wayfire. Bottom left, it's obviously QNFT, and you have there the Steam Deck, which runs GameScope for showing the Steam UI. So different things you can make use in WL Roots. Examples there for that. To even help you further with giving you a quick start if you want to write your own compositor with WL Roots, then there are, I just want to name drop some structs and functions which are central to the backend and front-end parts of WL Roots. For the backend, you got a struct WL backend, and you can create that, right, through a function call, which you get the WL display pointer. There are some common types which are used in both parts, backend and front end, like, for example, WL output, which wraps obviously in output and keyboard, and front end, where you have other types which you can also access easily through some creator factory functions. And one thing which you might stumble upon when you first look at the source code is that as a consumer, the libraries or the headers you want to include are actually all in one subdirectory, namely include WLR. So only in this subdirectory are the APIs you use for writing your compositor. Don't look at the other includes. They are internally for the other subdirectories in the include subdirectory. They are used internally by WL Roots. So that's a quick overview of WL Roots. Now, how are we using it in QNFT? As said, we use only the backend part for now. For that, so the first idea was to just use the backend part to show buffers on the outputs, right? Like talking to DRM. But we then quickly realized that we require session integration for that, because yeah, we want to become the DRM master. And it also makes sense to have the input processing directly handled by WL Roots because of this combination of lib input and DRM. And in the other backends, then there's also input directly written into the backend. So it makes sense to use all of that together. And yeah, the graphical output we have then also, basically we use our internal renderer to draw onto a buffer, which we allocate ourselves, and then we send it to the WL Roots backend via DRM as a DMA buff. And the goal now for the next month is to make use of WL Roots renderer as well. And the advantages we should be able to have from that is that we can then use something like direct scanout, for example, and currently WL Roots upstream is working very hard on further improving the renderer, and then also an integration with liftoff, so you have scan out directly in overlay plans. So there's just a lot of stuff in the future which we could then make use direct. We could direct make use of, so that would be very helpful, and that's why I think it's good to now look directly into how we can make use of the renderer as well. So yeah, as like 6 months ago, something like that, I decided, or yeah, something like that, 6 months ago, I decided to start with this WL Roots backend project. And as usually with bigger projects, I started with an issue ticket, and yeah, as I first only render backend, I got then feedback from Simon, so I expanded a little bit on it. I worked on a separate branch for that. And first I did a minimal vertical slice, so I can just start with getting something out there. And as said, I needed also session and the input through WL Roots, which allowed us to remove a lot of our own code, which is really helpful. And yeah, so in the timeline, I showed this also yesterday. Basically, WL Roots backend went from end of March to end of June, but still we now are in a phase where we do a lot more testing on the master branch, and we had already some fixes for standby and pointer gestures merge, for example, and also what allows us now to simplify the startup logic. So yeah, there are, as said, a lot of advantages for using WL routes, like slimmed down code base. Our integration tests now use the same code path as a live session, and we can work together with WL routes upstream. So that is also just good because we also, for example, have better communication and can share information better. And yeah, in a future ecosystem, WL routes would be a central part of it by having this windowing library collection, which I talked about yesterday. And as said, the next step now is to integrate the WL routes renderer. And we currently use our old render code as said, but the goal is to use the WL routes renderer. A little bit the challenge is that currently WL routes upstream is working very hard on the renderer to improving renderer, so we require some good planning and communication with upstream to get this going, right? And our old renderer uses desktop OpenGL, so we have to maybe rewrite some of the effects or at least adapt them so we can use the OpenGL ES, which the WL routes renderer uses. Yeah, and so I want to start with this work very soon after XDC, and I hope for the next release then we can already merge it. So that's the plan for the next few months. Yeah, thank you for listening, and I hope I didn't. There's still a little bit of time for questions.
There indeed is.
50 minutes?
Yes. Yep. Now, well, more like 8, but we're good to go. We now have time for some QA, but we're still waiting for questions from IRC.
All right. Maybe everything is clear.
Okay, Timur Christoph asks, to someone who doesn't follow KDE, what is the difference between KWin and KWin FT?
Yeah, so QuinFT was forked from Quin last year, so and it has the scope of what we want to do in QuinFT is a little bit bigger. So we want to split out some libraries and, for example, also improve collaboration with our projects like WL routes now. So that's the basic idea of it. If you are more interested in it, there was a talk yesterday I gave about QuinFT, like what the goals are of it and what we want to do next. So just check it out. It's in the stream, right? You already published everything from yesterday.
And one more from Timur. Also, is this going to be upstream to KDE itself, or is this a spin-off project? Although it was answered yesterday, I believe it's up to KDE devs at this point.
Yeah, so my strategy at the moment is to have this library split out of QuinFT. And from these libraries, when KDE can pick, right, I would, of course, try to advertise this as well. To the people who have some decision power in that regard, that some of these parts, right, when they have come to a certain degree of usability and stability, that then in the KDE default compositor, right, which is currently Quin, that this compositor then could make use of some of these split out libraries. And that would, of course, also mean that transitively, it would also make use of WL routes.
One more question from Sebastian Krzyszkowiak. As far as I understand it, WL routes renderer aims to support only the simplest use cases, recently even removed drawing with arbitrary transfer matrices, while KWin has plenty of effects, plugins, wobbly windows, things like that. Is it going to match well?
What was the last bit? I didn't get this.
Is the WL routes and KWin approach going to match well with each other?
That's a good question. have to look into that now, right? So I could now say, yeah, for sure, and blah, blah, blah. But in fact, I haven't looked into the WL roots renderer in detail yet. So that's something I just think the advantages are there if we can share the code. And if it doesn't fit the use case very well, then we have to think about extending maybe the renderer. The good thing is we have a good connection to WL roots devs, so, and they are always open for improving the WL roots code. So I think if there are certain things which are missing to make it work, then I would talk to them and hope we find a solution. Another idea is Wayfire is also a WL roots renderer, which is a floating window manager and has a lot of effects and plugins for that. So I want to also look into if there is possibilities for collaboration with them, right? So if there could be, for example, a library which sits in between WL roots and compositors like QuinFT and Wayfire, floating window managers with a lot of effects, which we could share, then that would be also great, right? If the scope of WL, if that's too much for the scope of WL roots, then we can find a level between. And yeah, that's something I want to start looking into as soon as after this XDC and the next release of QuinFT now is polished enough, right, to go out. So probably this month already, and at last next month after the release of QuinFT, after the next release.
Okay, looks like that's all the questions we have for today. Thank you very much for a terrific talk, and have a great day.
Yeah, thank you. Yeah, you too.
Hold on. Okay, and we're ready to go with the next talk of the day, TTM conversion in i950 by Thomas Hellström from Intel. Please welcome Thomas.
Thank you. Yeah, I'm going to hold a talk today, and welcome to this talk, which is about the TTM conversion going on in i915. It's going to be an overview. It's not going to be down at the code level, so that's really what you're going to have to expect. Yeah, and I will start with a short presentation of myself. My name is Thomas Hellström, as mentioned, and I started working with open source graphics basically on our spare time in 2003 with the VIA Unichrome chipset. It had a quite bad driver in what was called X386 then. Me and some other people fixed it up, migrated to X.Org. And I did some work in design then as well to handle the accelerated video decoding and also in DRM to support the accelerated video decoding as well, not so much 3D. At 2006, I joined Tungsten Graphics for Mesa work, DRM work, and X.Org, naturally. And Tungsten Graphics was mostly doing consulting for various vendors. We did some open source drivers, we did some closed source drivers, and contributed a lot to the DRM and X.Org infrastructure and also Mesa. Tungsten Graphics was bought in 2008 by VMware. So I joined VMware, worked there until 2020, basically with the VMware open source drivers in Mesa, DRM, and X.Org, and finally joined Intel in 2020, working now with the GEM and core team for i915 DRM. So the outline of my talk today, since most people are quite familiar with the i915 driver and what it is, I'm going to mention a bit about TTM. What is TTM? And above all, why is i915 adapting TTM? A bit about the driver structure, where in the driver are we introducing TTM, and why are we choosing that way of doing things? Going to mention a bit where we are today, some pictures. Talk a bit about what can i915 contribute back to TTM. Do we have a wish list for TTM moving forward? And finally, Q&A, some questions if there are any. So the first section here is what is TTM? It's going to talk a bit about features and history. And TTM started out at a time when DRM was very much different to what it is today. You had a global lock to grab the hardware. Some drivers had memory management in a very simple way. Yeah, and some other utilities to map that memory from AGP or from VRAM. No buffer objects, no fences, nothing like that. So TTM finally, after a number of iterations, ended up with a set of utilities to manage buffer objects and their placements in a way that the GPU could bind them and the CPU could map them. And it's all assumed that everything was done coherently. And actually, it was originally developed to support dynamic AGP binding. At that time, reading out from AGP was very slow, and I guess it still is. So the idea was that if we take the buffer object out of AGP, read from it, we could do that in a much faster way with CPU caching and prefetching. That turned out not working so well as we originally thought because of caching issues. But anyway, that's really how TTM started. And VRAM management was actually added as an afterthought. We concluded that, okay, some cards or some GPUs need VRAM support, so we add that as well. And some, of course, utilities to be able to copy from VRAM to AGP and back and forth, and also to system. But the set of utilities that we have today, they handle what I would like to call a hybrid trilock eviction or hybrid trilock evictions, which means that if we need to evict something to have place for other things, we need to lock that thing, we need to evict using trilock. And if we totally run out of objects to evict, we can do some waiting, simulating something that would look like a waiting lock, and then retry. We have command submission with wound weight locking and various options to select memory caching of the pages we allocate. And there also are some utilities for asynchronous evictions, which help speed up things during evictions. And TTM also actually pioneered, as I mentioned before, a lot of DRM components and functionality that Linux GPU drivers use today, but they aren't necessarily anymore in TTM, but they have been moved out to two separate components. For example, buffer objects, the main component for that today is gem. We had initially some variant of the deadlock-free weight die locking, which is very similar to wound weight locking, and also fine-grained locking around LRU lists, which wasn't the case for most GPU drivers at that time. They were using the big kernel lock or struct mutex. And the weight die locking was then abstracted out to the WW mutexes that we have in the kernel today. We had persistent memory mappings also at that time, which meant that you can evict a buffer object while user space maintains and still holds on to what it thinks at least is a persistent CPU mapping. Synchronization objects that later became the DMA fences, and also asynchronous migration. Unfortunately, TTM in the state today is getting old. The code is badly documented, and some design decisions aren't really what they should have been. So that's the sort of main drawback. But TTM has seen a lot of additions and cleanups over the years, mainly Red Hat, AMD. I think Oracle has done some stuff, and VMware as well. And it's currently maintained by Christian Koenig, AMD, who is doing a lot of cleanups to the code. So the big question here, why is Intel adapting TTM except because that we are starting to ship discrete graphics? Well, as background, i9-15 was originally implementing its own VRAM, or in the i9-15 nomenclature, local memory or LMEM management on top of the code for integrated. And that worked quite well, actually. And except for asynchronous migration, it supported mostly everything that TTM supports today. But on the other hand, we were diverging from DRM, where most of, if not all, VRAM-capable drivers use TTM. There was some actually considerable upstream pressure to see if we couldn't adapt TTM instead of reinventing the wheel, doing something Intel-specific. And it simplifies many things, like implementing asynchronous VRAM management and eviction. And it's also well tested, basically, because if somebody screws up, then most drivers using TTM gets some kind of failure, whereas, yeah, it's not restricted to a single driver. It gives us a chance also, of course, to contribute back and take advantage of the upstream development. And a bit of a curiosity here is that i9-15 was actually once the main target driver for TTM before going and choosing gem path instead. So looking at the driver, where do we introduce TTM and why do we choose to do it that way? And yeah, this diagram is a bit odd here because I quite soon realized that I was hiding the TTM glue bullet here with my picture. I had to redo it a bit. But anyway, we have the UAPI, which mostly is connected to the gem component here. We have the core component, which is mostly driver loading, unloading, suspend, resume, stuff like that. Some utilities for command submission and other things. And the GT component, which mostly talks to the hardware. Now the gem component has a number of backends depending on from where we want to allocate pages. We have the FIS backend, which is DMA mapped memory, which is allocated using the DMA API. We have the DMA buff backend, which imports buffers from other drivers or from other instances of our own driver and exports them. And we have the system backend, which actually takes pages from shared memory objects and hands them to the gem component. And we choose here to hook up TTM as a backend, as a TTM backend, to allocate LMEM or VRAM pages. And for discrete, we actually use this also for the system pages. So the question remains here now: why did we choose to do it this way? Why didn't we just say, okay, we replace gem with TTM? And the short answer is actually there's two short answers. One of them is that we have discrete. Integrated GPUs as well that still will need to use the system backend before porting that over to TTM if that's going to happen. The other answer is that we have some code or quite a lot of code in development that uses interfaces from within the gem component that we might break by doing a very invasive TTM changeover. So this was the path chosen. What we will end up with perhaps in the future is something looking like this. The UAPI talking more or less directly to the TTM GLOW, which in turn uses the core code and GT code for communications with the hardware. We have done some important UAPI changes for discrete GPUs. First of all, CPU maps will use the TTM provided address space offset when mapping buffer objects instead of requesting its own based on the caching that user space wants. And this also means that user space has to live with the caching mode that the kernel driver selects for it. And that in turn depends on whether or not we're choosing to allow LMEM in the placements or just system memory. And user space gets to choose the memory region placements of a gem object. They can choose to allow it only in system, only in VRAM or LMEM, or it can actually give a set of any memory regions where the user space object is allowed to be placed. Some IOPTALs are gone. For example, set caching is completely gone. Set domain is mostly gone. It's used by some user space drivers or user space components to wait for GPU rendering, so that functionality still remains. Relocations are gone, and we also have seen a bunch of other UAPI cleanups by Jason Ekstrand that's happened also simultaneously in Mesa to remove a lot of unneeded functionality. And I also often get the question, is gem or TTM the fastest choice? And I would like to say that it's not really a matter of TTM or gem in any way. There are other much more important factors at play. For example, caching. Reading out from a cached buffer isn't the fastest way of doing things. An uncached buffer isn't the fastest way of doing things. And I mean, if some user space ends up doing that because of the change caching mode for TTM, that's something we need to fix, and that will of course make TTM look slower. Page allocation is another thing. For example, allocating pages using shared memory objects is quite slow compared to using the alloc pages API in the kernel, which TTM uses. And synchronous waits is something we would like to avoid as well during command submission and other things. And TTM provides a very good way to avoid those, which you, of course, also can implement in the gem framework if needed. So as an answer to the questions raised earlier here, it's not really about gem or TTM, it's about other things. So where are we today? Yeah, I have a little video here of the most recent development. This is a DG1 system. Yeah, it's not really anything interesting, and it's better viewed, I guess, from the link in the presentation material. What we're doing here is starting up 2 instances of the Valley frame, of the Valley benchmark, and also a super tax card, suspending, resuming, and things look okay and with decent or at least reasonable frame rates. So yeah, that sort of answers a bit the questions where we are today. Let's see here. DRM tip for i9-15 for DG1 is, yeah, I would say fully functional except suspend resume, which is under review. We have some locking cleanups in the pipe. And we also have TTM shared memory support plus shrinking in the pipe, also out for review. And that is a way to avoid the watermark swapping in TTM today, and instead use the kernel shrinkers for that. I know that AMD and Christian Koenig is doing some work to have TTM support that natively. Meanwhile, we sort of start out with supporting that with shared memory in our driver today. We have fully fail-safe asynchronous migration and eviction also in the pipe, also out for review, and it's being worked on. DG1 support is in Mesa main, and as you can see, it works reasonably. Desktop and games are working. There are still some occasional crashes being looked at, and X-Wayland isn't working very well at the moment. That's also something we need to look at. We need to fix up CI tests for UAPI modifications, of course. A lot of the DG1 CI has been very red for quite some time. That's mostly due to the UAPI modifications. We're fixing that up as fast as we can. But even when that's done, we need some more CI test coverage for the new functionality added. And also that would be able to cover more of the TTM module itself. So another question that I get a lot is, what about TTM for integrated? And we haven't really fully decided on that yet. In its simplest form, it's a matter of pointing also integrated to the TTM gem backend rather than the gem shared memory and FIS backends. And particularly after the work being done by Matthew Old now, with shared memory being supported by TTM, this would be something quite that could quite easily be enabled. But one thing with the integrated support in the gem component today in i9-15 is that it uses CPU maps with conflicting caching, which means that it's basically tied to Intel processors, of course, because it uses some functionality that is not guaranteed by other processors. And the question is really here, can we support that with TTM in a way that looks okay to both TTM maintainers and to us going forward maintaining the i9-15 driver? And one way is to lie to TTM and say, okay, we're only using the objects as kernel objects, and TTM doesn't have to care about the CPU mapping to user space. But behind TTM's back, we do that ourselves. But that's not very pretty, but it's a way to go. So the answer to the question, are we going to support TTM for integrated? I guess we'll have to wait and see here a bit. So another big question, how can we contribute back to TTM? Well, CI and bug fixes is one way. If somebody breaks TTM, they would also break DG1 CI at the moment, at least in the parts that we're using. Bug fixes, of course, as we port things over, we discover bugs, or CI discovers bugs. We'll add more reviewers and developers, and reviewers and developers that are sort of familiar with TTM. Hopefully, that contributes to more valuable discussions on DRI devel. And code-wise, we have a buddy VRAM or LMEM allocator that's been ported to a TTM resource manager, which means that it's sort of reusable for any driver wanting to use that functionality. As for the future, wish list from i9-15 to TTM is something that we actually work on a bit ourselves, or at least started some prototyping. And that is full wound weight cross-device locking during eviction. The cross-device is sort of optional to begin with. But anyway, that was something we had in the i9-15 driver before the TTM port, and that we would like to have the TTM port support as well. That means basically we don't try lock when we evict. We do a full waiting lock if that's really, if that's something that we would like to do because we think it will succeed. We would like to have kernel shrinking rather than watermark swap out, and that's a bit complicated in TTM because to be able to do that, you need the data in a shared memory object, and data that's in uncached system pages or even in DMA allocated memory needs to be copied, and that happens during the shrinking itself quite late, so that's really a problem. But I think AMD is working on this, and hopefully we can get that sorted out, perhaps with some Intel help as well. So that leaves us, I guess, to the Q&A. Guess the presentation is done.
Okay, we're now waiting for questions from the IRC. Jason Extrent asks, regarding TTM and the maps, Mesa no longer switches mapping types, even unintegrated. Switching would break all the MESA, but be fine for now.
So can you repeat the question there?
Maybe it's not a question, it's just more like a note from Jason Extrent.
Okay. Understood.
And Huang Rui asks, have you encountered the performance problems while the TTM is always doing the eviction at the backend? If yes, how do you handle this?
I don't think we have any eviction performance problem as far as we can tell. Rather on the contrary, actually, because of the asynchronous eviction.
Okay. We could wait for a little bit longer for questions, maybe? Okay, looks like we won't have any more questions for today. So thank you very much for the talk, and please do visit the IRC channel in case someone... Oh no, we have one question from Bas Nieuwenhuizen. How are you dealing with the out-of-memory killer on TTM compared to the old path?
That's something that we really we haven't really tested that and compared yet. I guess that will be a question that we will be more able to answer in the future.
Okay, and that's all we have for today, I believe. So thank you very much for the talk once again, and have a great rest of the conference.
Okay, thank you very much.
And we're halfway through the final day of XDC 2021. Coming up after the break is our final workshop, X.Org Security Birds of a Feather, continuing discussions from yesterday talks by Matthew Herb. Link to the workshop's Jitsi is in IRC. In parallel to the workshop, there are 3 talks, starting with Benjamin Tissoir, status of FDO, GitLab, or cloud hosting. See you in 20 minutes. And we're ready with another talk of the day, Status of Free Desktop Org GitLab Cloud Hosting by Benjamin Tissois. Benjamin, the stage is yours.
Thank you. So thank you for attending this talk about the state of GitLab on the cloud, what happened in the previous year, and what's gonna happen in the next few, in the near future. So I'm Benjamin Tissois. You can find me with Bentis over IRC on FTC. I'm a free desktop admin, as most of you know, or some people know at least. And this is a follow-up presentation of the one I gave last year. For those who were not here last year, I have a 1-minute short summary of what happened last year. So if you look back at the slides from last year, in January 2020, the treasurer, Daniel Vetter, came back and say, hey, we're having a $6,000 bill from Google for this month. And if we keep growing that way, then you are going to have to shut down the CI. So the treasurer was not happy. Everybody was not happy. Some people like me were involved into writing some new tools. We got Docker free space introduced. The artifacts were chased down with many project leaders. Thanks a lot for them. And then we also wrote some Git cache for Mesa. And all in all, this all reduced the bill from 6,000 to 3,000 months. So we are happy. But since there, a lot have moved. And so this presentation is mostly understanding what we did for the past 12 months to actually reduce the bill and where we are now and what's the future. So first and foremost, I think everybody is interested in those numbers. This is how much we spent for to pay for the GitLab hosting for towards Google. So this is money that is taken from the organization. As you can see, there has been several periods. The first few months where we were at 3,000, a little bit more, and then we suddenly started to fall down. So what actually happened during those times? So between September and February, as mentioned previously, the heat was gone. The treasurer was saying that we are in a much reasonable state. But if you look at the number more carefully, you'll see that they are slightly increasing. They are slightly increasing, not so much because of we are not good at doing what we do, but there are more and more CI involved, and more CI involved more download, more and more cost. So it was time to prototype a better solution. Also, if you remember at the very last slide of my talk last year, I was telling you that Equinix Metal, which was Packet.net at the time, allowed us to, and they afford us to host our own cluster on their platform. So that's what we plan to do during that period, and we try to prototype a solution. We self-inflicted 3 constraints. The first one, which is not so much of a constraint, but anyway, was to keep the container registry in Google Cloud Storage. At the time, it was 6 terabytes of data, which means that it would have been slightly difficult to bring back in-house on a non-very, I mean, we had too many unknowns in terms of storage, too many, anyway, it was kind of difficult to bring all this data in-house and not being sure that it was reliable enough. We also wanted to have something equivalent to Google Cloud Platform. We were really happy with the Kubernetes deployment that we were having previously. But there are a few bits here and there with the Google Cloud Platform that allows us to have something which is really nice to deal with when you're a sysadmin. And last but not least, we wanted to do the migration to the new cluster without much downtime. We didn't want to impact the various projects hosted on gitlab.freedesktop.org. And so that required us to add some quirks to be able to make sure that we do the transition while it's still up. So in January 2021, I finally got a prototype for that new cluster. I used K3s as a base. for two reasons. The first one is that it's already something that we were familiar with because the Git cache that I mentioned previously was already deployed through K3s. And also K3s is really simple and easy to deploy. K3s is a project by Rancher, owned by Suzy now. So they are good guys anyway. We are relying on 3 machines from Equinix Metal, 1 server, which is called the control plane in the Kubernetes world, and 2 agents. To keep some sort of confidentiality with between the cluster and the rest of the machines that we have on packet, we decided to use a WireGuard for the internet communication. We also used Ceph for anything that is deemed light in terms of size, but where you actually need to have a lot of transactions. So that would be for Git and database. Ceph is a distributed file system that you can plug in on Kubernetes very easily. And for everything that would be heavier, we would use Equinix Metal Elastic Storage. So that would be for the artifacts. Artifacts are not very they are important, but they are not critical in terms of access time and all this kind of stuff. So Equinix, the Elastic Storage there is the same kind of things that we have on Google Cloud Platform, when you can attach a disk for a size. You just have to pay for it anyway. To be able to have node on time for the transition, we connected 2 clusters together by using a project which is named Kilo that basically creates some WireGuard entry points between clusters. And also to be able to make it transparent for people, we use some custom go-between tunnels to link service together. Go-between is really a netcat. However, there are 2 pieces that you don't that you have on Google Cloud Platform and that you don't get if you just deploy some bare metal Kubernetes. The first one is the logging. Google Cloud Platform has some very nice logging mechanism in place. You don't have anything to do. You just create your cluster. You got all of the PCs together. You've got the database, and you can work through the database very easily. To get the same equivalent thing, I deployed a thing which is called EKS, which is the Elasticsearch stack. So it's Elasticsearch, Kibana, and some other bits here and there, which seem to be working well enough in the deployment, in the test deployment. So we started by using that. The second problem of the second thing that we get from Google Cloud Platform is the redundancy of the main server. Everything is backed up within Google. And actually what we have right now, I mean, in January, we had to emulate all of these Kubernetes facilities with the control plane in-house, and we were having just 1 server doing that. So that was a little bit problematic, but we had to move on because I was seeing the numbers going up and couldn't really wait too long for that. So at the end of January 2021 and beginning of February, we started the migration from Google Cloud Platform. Over 2 weeks, we moved all of the Git repos from Google Cloud Platform to Equinix Metal. We also moved most of the artifacts. We moved all of the jobs logs, and also a couple of months before the migrations for all of the artifacts per se. And on a Sunday, February 7th, we shut down the service on Google Cloud Platform. We did the DB migration, we updated the DNS, and we put it back together. And then the next few months, we gradually killed the services on Google Cloud Platform. It was very enjoyable, and we removed the nodes. So this is why on February 2021, there is a big drop in the bill from Google. We were not using Google Cloud Platform anymore. We were just using some storage there and some VMs for most of the things. So you can see that it was pretty efficient from day 1. We were really happy about that. The treasurer was really happy about that. So that was good. That was good. And you can also see that as we kill the VMs, the cost gets down by 600, 5 to 600. Okay, so that leads us roughly to between March and May 2021. I was actually a little bit worried at the time because we were not having this high availability control plane that Google Cloud Platform was offering for free. It was even worse because the control plane, the server, had no backups in the same way, in a way that we could not put it back together. However, GitLab has the backups. We are running daily backups of the entire GitLab server, which means that if we would lose the cluster, we would have to bring it back together from scratch, which means probably a couple of days or more realistically a week of work where no other project can work on GitLab and they cannot accept merge requests and all this kind of stuff. So that was not comfortable. So what I did was doing my research. I discovered a few projects. One of them is KubeVip, Kubernetes Virtual IPs, which allowed me to understand a little bit more about what is BGP and how it works. In the meantime, K3s got improved for the high availability control plane part. And I started prototyping a K3s cluster with high availability control plane. And that's where I had one of the scariest days of my life, I think, where basically on May 11, or May 12, something like that, right before going into vacation, I remember I was testing the automated deployment of the cluster. Of course, I was doing my automated deployment, making sure that it was working, writing some docs. And at the very end of the day, I was like, okay, I need to do the full deployment to see if it's working. And so I followed the fresh documentation, deployed test cluster onto the production cluster. Immediately after, I saw that GitLab was done. And if I logged into the production cluster, nothing was working anymore. We didn't have any disk, we didn't have any workload, we just had fresh cluster. So it took me a little bit of time to calm down, to think through of what happened. And it turns out that the data was not lost, it was only hidden or not used. If you deploy K3s without the high availability control plane, basically all of the cluster state is stored in a SQLite database. If you deploy it with the high availability control plane, basically what happened is that you're using an etcd database. So, and the thing is, K3s would not destroy the data whenever it was redeployed. So I was able to tear down the cluster, back up everything, tear down the cluster, redeploy a new cluster, refresh the SQLite database with the backups that I did, and everything was backup. I was really happy. I think the most funny part of the day was that people were actually thanking me for fixing things while actually completely killed the cluster in the first place. But yeah, I took the praise. Thanks. That gives us to the second part that was very worrying in the choice that we made previously. At around that same period, I realized something, and I immediately emailed our Equinix Metal sponsor. I realized last Saturday that the Elastic storage is going to be decommissioned very soon on June 1st. We were 3 weeks before June 1st. I can't thank them enough because their answer was the following. I think your approaching of expanding your cluster to include more local disk is the right option. Feel free to leverage some S1 machines or additional M1 to help you make it happen. To give you an idea, S1 machines have 12 hard drives of 2 terabytes each, which means that basically they gave us the keys to some very, very large machines that we could use to store all of our data. So thank you a lot. Not sure if you can see the animation with the screen sharing, but we were really happy with the Equinix method. So thank you. So at the end of May, I've got a new prototype. I've got 6 machines now this time, 3 servers, 3 agents. It was using K3s high availability, using KubeVit, the project I mentioned just previously, BGP, of course. It was fully deployed with a Python script. It was also using Minayo cluster for saving the artifacts. This is a file serving project that worked really well for the Git cache that we're using. So why not using it? And we are using some dedicated Elastic IPs for GitLab and the other service because we can now. On May 24, we put the new cluster in production. We actually did the migration, the Git migration, a couple of weeks before. Nobody noticed this normally, I think. And on May 24, we shut down the cluster. We did the DB migration. We put it back up in the same way we did the previous migration. We were really happy for 5 minutes because Minayo immediately started to show some weaknesses in the artifacts upload. A lot of people were starting to complain that their job was successful, but as soon as the artifacts were involved, they were trying to upload the artifacts and the artifacts were failing. So initially we thought that this was because of the because we were still syncing the artifacts that are between the previous storage and the new storage. But after a couple of days, we realized that it was not the case anymore, and Minayo was just doing things plain wrong. So we had to go back to the drawing board, and we ended up selecting Ceph object storage as a replacement. I already mentioned that we're using Ceph for the file system over Kubernetes, and turns out that Ceph also have something which is called Ceph object storage, which is the exact same thing that Minayo. It's an Amazon S3 API that you can use in Kubernetes or in other cloud environments, and it works just fine and even way better than Minayo. So after one small week of testing, we put it in production, and immediately after, it was way better for people. So first week of June 2021, the cluster was back up. It seemed much better, but we actually lost all of the artifacts data for the previous week. Excuse me, I just saw an IRC, Daniel making fun of me. So the artifact data for the previous week was lost because of an issue with Minayo. I thought that the Minayo was actually safe and I would be able to shut down one of the machines, and turns out that it was not. And so we lost all of the artifacts. So if you look at the numbers, you'll see that there is no impact on the Google Cloud Platform bill, of course, because the Google Cloud Platform bill only relies on the registry cost, which are completely unrelated to this migration. But however, you can see that the entire the global cost is still decreasing, and that's because we tried to make it happen by deploying a Docker cache. The Docker cache is located at registry-mirror.freedesktop.org, which means that it's local to the Equinix Metal machines that we're having. And actually, if you're having runners, it would be nice if you could make them point at this particular URL instead of the registry.freedesktop.org. What we do in the FreeDesktop runner, we just override in the /etc/host the IP, so that they are told to use a cache, and so it saves us a few bucks. It doesn't work completely as expected. Sometimes it just fails. You have to keep the process once or twice, like today. But still, it allows us to have a sub 1,000 amounts Google bill. So the treasurer is happy. I hope that Daniel, you are happy. And so, yeah. So after this long introduction of what we did for the past year, we're gonna have a look at what we have now. So I think this is one of the most important slides of the talk. This is what Equinix Metal sponsors and what they gives us for free, which represents a whooping $13,000 a month. So we are having three operations, three main operations: the Kubernetes cluster, the various runners that we run for the CI, and the one weird thing that we have Minio packet .free.org that is using for the Git cache that I mentioned previously. Okay. So even if, so yeah, again, thanks a lot, Equinix Metal. We can't thank you enough. This is a huge step for the community. We really appreciate that. However, we're still having some issues. Some of them are partly solved, as since I started working on the slides and know that it's already 2 weeks in September. But let's go into that a little bit deeper. The first one, the logging and the metrics were not really stable. What happened was that it was working, so Elasticsearch and Kibana was working well enough until we are actually using a lot more data right now. It was up to the point where we were able to store only like 3 days of logs inside Elasticsearch, and it was immediately broken. So if we were not here to prune the logs and to ensure that it was working fine, and every time there was an issue, whenever we have to go to the logs, then the logs were not here, so we can't solve the issue and get it there. So beginning of September, I decided to switch Elasticsearch to use Loki, which is a project by Grafana, to just store everything from the Kubernetes logs, but we would keep still Elasticsearch from everything that needs to be deeply tagged, so we can do a quick search amongst all of the errors and all this kind of stuff. It's still in progress because I still need to implement some data retention rules. Right now, we are just logging everything and wait and see how many days of logs we can keep. But this is something that that is working already very well. The next topic, which was the most seen by the community, was the 502s that we were having periodically, usually on Monday morning, in the while the backups were running, or at least I blame the backup. It seemed to be related to network when we did the initial test, because a heavy traffic on the object storage on Ceph object storage tend to kill some of the disks. And the problem is that when you kill the disks, the Ceph cluster entirely gets like lost and needs to rebuild itself, and there is some watchdogs that are in place, but yeah, it takes 15 minutes roughly to get it back together. And my idea was that WireGuard was a probably good candidate for mixing up the network. Whenever you write something on the Ceph disk right now, today, you encrypt the data 3 times because we have 3 times redundancy for all of the data. So maybe that's not the best solution. There's the possibility that there is another culprit, which is Ceph directly, because all the time it seems like it was related to some Ceph nodes crashing. So if it's network related, we've got some action planned with Daniel Stone, and that would be to create some VLANs on Equinix Metal just for Kubernetes. Equinix Metal allows you to create VLANs directly and connect them to the various machines that you're having. And we would be able to isolate the traffic and rely on the VLAN for the privacy instead of rely on WireGuard. So, and see if that helps. By the way, if anybody is interested in looking into that, and if they want to play with us with K3s, Kubernetes, and whatnot, we would be glad to add 1 or 2 more people to the team. The other option was that it was self-related, and actually it's something I did last week. I actually read the docs on Ceph and realized that I haven't read it properly, and I had to tweak the memory requests and limits for Ceph and disk. Since then, we only had 27 errors in the past 8 days, and that is to compare to the last time the ORM killer came in and gave us 35,000 errors over 30 minutes. So what happened was that the process that was monitoring the disk thought that they had the full amount of RAM available to them. But when you have 12 disks, you have 12 processes fighting for 256 gigs of memory. At some point, the memory killer comes in and say, well, nope. It just kills the process, and that puts a mess in the cluster. So by tweaking the memory request and limits, it actually ensures the process know, hey, I only have 4 gigs available, not 250. But yeah, I still want the previous part done because that would be awesome. So please help. Okay, so that is something directly towards the board. We want to have an entirely sponsored bill for the cluster, or at least I want. Would be nice. So can we just ditch Google Cloud Storage for the registry and rely on our own cluster to serve the registry images, the container images? So in theory, yes, we have enough space for it. But last year we were having 6 terabytes of data, and today we are having 10 terabytes of data, which means that we are growing way too much for something that we can't handle in a local storage. So there is an ongoing plan, actually, from GitLab to change the registry architecture that we could use. Right now, if you have a look at the registry, the way it's working, it's a file system based. So whenever you try to walk through all of the list of the containers that are in a particular registry, the registry server would access Google Cloud Storage for every single manifest that you have, for every single tag that you're having. This is less than ideal, and we're having 10 terabytes of image. You can imagine how nice it is. So what GitLab is trying to do is they are trying to use a proper database, which would allow something to, so in terms of, we would have some performance improvements, I expect, but we will also be able to use some garbage collector while the registry is working and in read-write conditions. GitLab is taking care of everything. They are taking care of the migration also. They are writing some great plans on how to do migrations. And turns out that we will be able to serve both registry at the same time and do the migration one by one without having anybody noticing that there has been some migration. So we'll use that opportunity to bring back our data in-house and to reduce the cluster bill. So in summary, it's scheduled for late 2021 if time permits, and if GitLab manages to enable that, which is not sure because they were supposed to start this summer, and I haven't seen anything yet. However, if anybody wants to be involved in the sysadmin team or in the broader GitLab team, we need some scripts to choose which image are still valid. So you can do that at your own project level. You can clean that up. But if you're using CI templates, then you can do that in a generic way because CI templates add some tags to the to the various images that we have. And if you look at them, you can know whether the image is supposed to be trashable or if it's something that we have to keep it forever. So you don't need to have any strong Kubernetes knowledge, or all we need is people with some scripting knowledge, being Bash, Rust, or whatever, Go even, because you just need to talk to the registry. It's a simple API. You even have some tools like Scopio to talk to the registry. So we just need some good help. Okay, next thing that we need to do are integrating Minayo packet into the cluster. Okay, if you look at the slide from a little bit time previously, you can see that there is this one Minayo packet.freelancer.org, which is one large, extra large system, which seems very similar to one of the runners. And basically what we did was create one more, extract one runner from the pool. So if we can manage to integrate Minayo packet into the cluster, we will have one more runner without Equinix Metal noticing that we are using one more runner for the machine. So that would be nice. That would not inflict a new burden for Equinix Metal. However, there is some issues, and the way that the thing that we are deploying right now is Minayo and OPA there. And so far, as we already saw in the previous slides, if you were still awake, Minayo is not working very well with a new cluster. There are a lot of issues there, so not an option. So we could rely on self-storage, but self-storage doesn't work properly with GitLab JWT tokens. That is an issue because that's the way we used to authenticate with the storage. That's very convenient, so we need to find a workaround that. And last but not least, OPA, which is Open Policy Agent, I should have put it in the slide properly, is actually, if you enable that in Ceph, it's supposed to be working, but it turns out that there is a segmentation fault and there is a config. So yeah, we've got some work to do. As of today, the current solution, and which is not entirely prototyped, is to use Keycloak to convert the GitLab token into Keycloak token. That would also leverage some other facilities from our cloud hosting. Keycloak is an identity provider, so we could rely on Keycloak to have some fancy other things that I actually don't know about, but that would be very nice to have. To solve the fact that OPA is crashing our configuration, there is a solution which is put a proxy in front of Ceph object storage nodes, the pods, that would talk to OPA and validate or not the request. So Istio seemed like a good thing. And as in the previous steps, if anybody wants to get involved with Keycloak, OPA, Istio, and Kubernetes, all of the fancy new keywords, I would be glad to give you a crash course on what we currently have. Okay, last but not least, this is something that would be very nice for us. That would be if we were able to include the runners in the cluster. Why the runner are still manually administered? It was automatically deployed. It's automatically deployed though, but that also means that the change in the configuration requires some manual intervention. Also, whenever we upgrade the various runners, we need to upgrade them manually one by one, and so that's a lot of time spent for basically nothing. The other thing that we'd like to have is metrics. They are twofold. It would allow us to know whether the clusters and the CI is underutilized or overutilized. And it actually, at some point, I had one runner inside the cluster, like just to see if the metrics were working. And turns out that it allowed me to realize that somebody was actually using our CI to do some Bitcoin mining. So if we were able to have some metrics from the runners directly, that would be really, really nice. However, there's one thing that users from GitLab that freedesktop.org needs to be aware of is as soon as we do that, we won't be able to have privileged runners anymore, which means that Docker in Docker will not work in the near future. If you're using Docker in Docker, it's working, but it will not at some point. If you use CI templates, it will continue to work because we will ensure that CI templates work. The reason is because CI templates can work in a Dockerized environment when Docker in Docker actually needs to have access to the host. We also need Minayo packet to release its machine, so we can actually not add one more machine because we already think that we are using a lot of Equinix metal. So that would be nice if we could release that first. So we've got some actions there. We need to deploy we need to write the Kubernetes deployment for them. We can't really use the Kubernetes deployment from GitLab because there are some things that we don't like the fact that every time it recreates a pod, there is a new runner registered, and we like having things stable. Also, we would like to ensure that the runner jobs are on a different VLAN than the main clusters, and they are not capable of accessing the cluster at all. This is something that needs a little bit of investigation. Okay, so we are approaching the end of the talk. Prepare your Q&A if you want. But there are a few lessons learned from the past year. The first one that I learned for the first few months last year, since last XDC at least, was that Google Cloud Platform gives a lot of benefits. You get logs for free, you get a lot of things. You don't have to care about virtual IPs, you don't have to care about a lot of things. But it comes with a cost, of course, that you have to pay for it. So I think that we are still not in a perfect cluster environment because we are seeing some errors here and there, and it still requires a little bit of maintenance from time to time, but we're getting better. Last week, I would have said that we are not in a perfect cluster environment at all, but now we are almost there. I would like to take 30 seconds to 2 minutes to thank the Free Desktop community, at least the people on Ash Free Desktop from FTC. Every time I mess up pretty badly, nobody complains. I think last week, only one person complained about 5020, and it was immediately shut down by so many others from the community. So thanks a lot for that. I really appreciate that. If anybody wants to get involved, the community around the admins is really nice. I mean, I don't think that we sysadmin bites, and and the rest of the community is very nice. So that's a very welcoming place. And last but not least, I would like to thank once more Equinix Metal for their support there, because without them, I'm pretty sure that we would have to kill the entire CI and the entire GitLab because it was way too expensive for the organization. So that's it. And now I'm open to any questions that you may have or may not have.
We indeed do have some. And Martin Ruka has not a question, but just wanted to say in the stream that he cannot overstate how much of a hero Benjamin is. He had a taste of what 1% of his work when failing at deploying Indico in the cluster, and you were so nice and helpful.
Thanks.
So you have a fun club. So, ladies and gentlemen, please come and help volunteer some time to help Free Desktop Org.
Yeah.
And now we have 3 questions. First from Simon Sir. What makes Minayo not work on the new cluster exactly? Something not fixable.
So on the new cluster, what happened was that I was using. So on the old. Oh, let me. Okay, so in the Minayo packet, Minayo is working really fine, except that Minayo, the way that we deployed it was Minayo single server. It's you just run one process, it has access to the disk, and it's working very fine, very well. On the new cluster, we wanted to be able to shut down any machines at any time. So we deployed Minayo cluster, which is a new variant of Minayo that basically allows you to have several pods on several machines that where you can actually talk to the various, you talk to one of the service and it would propagate the data across all of the machines that you have in the cluster. The problem is that the mini-IO cluster right now, the way it's deployed, doesn't have access to the topology of the Kubernetes cluster, which means that what we had was that instead of having an event replication across the 3 nodes that we were having one node with all of the data, with all of the pods related to the mini-IO cluster on the same node, which means that whenever this machine was taken down, it was completely, the cluster was completely lost and didn't know how to work. In the same way, whenever we were hammering the mini-IO cluster with the artifacts, the mini-IO seemed to be really lost in what it needs to be doing. And it was not well working enough for all of the heavy workload that we have. So maybe we can fix that, but I'm afraid it's way out of my league.
Okay, and one more question from Daniel Vetter. We're using QEMU to run cross-compiler ARM unit tests in IGD. Will that keep working with CI runners in the cluster?
Yes. So the privileged runner would mean that the runner will be running in a sandboxed environment, properly sandboxed, but we will still export VKMS, DKMS, or whatever. I mean, we will still export the various card. We will still export the various. No, it's not VKMS. Sorry. We will still allow the QEMU to run properly there. The only thing is that if we run the in a non-privileged, in the privileged environment right now, you can get out of the sandbox, access the files to the cluster, and actually directly talk to the various nodes in the cluster, which is not something we want from the runners. So we will ensure that we'll keep the service. The only thing that will shut down is the current Docker, as far as I can think.
Okay, and it looks like that's it for questions for now. So thank you very much for your excellent talk, and I'll see you in the IRC in a moment. Thank you. Have a great day.
Thank you.
Okay. And we're ready to go with the next talk of the day, making bare metal testing accessible to every developer, presented by Martin Rucola ni Perez. Martin, the stage is yours.
Thank you. Sorry for the quick enabling of the webcam. So, who am I? So yes, changed my name. I used to be called Martin Perez, but I got married like a month ago, and now my name is Martin Rucola. That's a very Finnish name. So I'm now also a freelancer at NewProof TMI. TMI is just basically well, a type of company in Finland, and I am a Valve contractor. And I used to work on Intel graphics and Nouveau. And well, I guess that's about it. Oh, I used to be also XORG on the board of directors, and I'm somewhat of a FDO admin, very, very part-time. So why do we want to have test farms, bare metal test farms? Well, here we go. So with GitLab, we got unit testing for all the drivers and being able to test building them. So that's wonderful. However, it won't prevent all the regressions that could happen. We could emulate the hardware, especially as part of the tests, but the models are not perfect. I mean, the hardware is pretty much, I don't know, 50% of the code that is being executed. It's just that this code is something you can't change. Hardware here also involves firmware. So in the end, the users are not running your model. They are running on the actual hardware. So we need some level of integration testing. And since the hardware is not in the GitLab public runners, then at some point someone has to do it. So, okay, why not you? Well, one reason that could motivate you to do this is that the farm could improve your productivity, your personal productivity. So, any kernel developer is going to have anyway one machine that is the development machine, and then one where you actually test your code. There are some people who don't do this, but usually this is how things go. So one advantage also of having a farm is that you could test your changes on more hardware generations in one go than just the one that you would be going there, deploying your kernel, rebooting, blah, blah, blah. Also, you could debug issues using interactive sessions from your main PC rather than having to go to another one, you know, take the keyboard or having a KVM and switching, pain. And then one benefit also is that if you have a good farm, you could let your colleagues test their changes on your rare hardware, something that they don't have. And that's beneficial because that means you don't become the unofficial maintainer of the rare hardware you just got because there was one reason at some point. And that means that it spreads the load of keeping this hardware working. Then, so conclusion, because it's good for you and for the project that you're working on. So in order to really make it better for you, there are quite a few requirements that need to come. The first one is that it needs to be more convenient than whatever the current developers are using. So it needs to be easy and fast to add a new machine to the farm. Should be very easy to switch the hardware in the farm, as in like switch GPUs without needing a manual reconfiguration of it. You need to have full flexibility in the deployment. That means that the infrastructure that you have should not limit you in any way. You should be able to deploy whatever user space you want, whatever kernel you want, things like this. If someone is using your test machine, when they are done with it, it should be as if they had not touched the machines at all. Then maintenance time should be limited to, let's say, an hour per week. Otherwise, it's just too much work. And then at some point, you're going to have a week that you won't have time to do any maintenance. And then you won't necessarily have time to go back to it. So the farm just gets unmaintained and becomes not only useless to others, but also to you, and also to potentially add noise to the CI results. Another aspect is that the farm needs to be highly available. So that doesn't mean that you need to be living in a data center. You just need to be resilient to short power and network outages. And well, if your ISP cuts your internet connection, or Comcast just kills your optic fiber somewhere in the street, then well, that's what it is. We have redundancy for reasons. And if you look at what happened during the summer with OVH, where the entire data center in Strasbourg just got on fire, then I guess, see, it's not different. And yeah, talking about fires, there should be minimal risks for your flat house or building. That's somewhat of an important aspect. So we're going to go through a couple of solutions that all together enable making a farm easy to use. So the first one is to use containers, not to have OSs that you install on every single machine. So we've been working on the project called Boot to Container, which is an initram FS that has a declarative interface. You basically just say in the kernel command line what you want to boot and how you want to configure the machine, and that's it. It's not complex. So that means that you don't need to install, maintain, repair the test machine's distros that just happen to get corrupted or whatever. Also, that means that every boot is fresh, and you don't have leftover files from a previous run or something like this that is going to affect you, because everything is run in containers. But of course, if you want to use some or share some data between the executions, then you can use volumes for this. And since basically it's a cache, you better also back it with something like Minayo. So as if you want to restart a job later or something like this, then you can get back the files that you had and then continue execution. Also, one thing is that unlike just booting with NFS or something like this, where every boot will basically download every file that you need, when you use containers, then you have the different layers that can be cached on the test machines themselves. And that means you only download the changes or the overlay that is missing for this particular run, something that if you were to change, I don't know, a couple of files, then you would just download the changes basically, or the new files, as opposed to downloading the whole disk image. That means that, well, you can basically be up and running in 5 seconds. That's pretty fast. And that's the point of using an initram FS. That's the smallest distro you can make. And also that means that you can reuse the same containers across all the machines, including the ones you've made, including CI. So you can standardize on this. So no need to make a root FS for your test machines. You can have just a container that you build in your GitLab pipeline, and then you deploy it on the test machines. It's very cool. Next, you need to automate absolutely everything. That's the only way to manage this. So, for instance, the deployment is done through Pixie or Network Boot. Then there is this concept of auto-enrolling. So the reason why I put this Surgeon Hartman photo there on the right is because this is the name of the project in our infrastructure for enrolling machines. So if you haven't seen Full Metal Jacket, then you're missing out on the joke. But it's a drill instructor, basically. So what does it entail? It entails auto-discovering the hardware. When we first boot the machines, there is a default target on the network boot. And this one is just going to be registering the machine with the executor. Then after this, it's going to look at all the hardware that is in there, which GPU you have. Well, it can be anything. It depends on your job. In our case, the only thing we care about is what is the PCI ID, what hardware generation it is, or family, or code name, and then we just create tags for the machine. Then we run 100 boot loops, and we check that all of them succeeded. And if they did, then the machine is auto-exposed to GitLab. And on GitLab, the machine is exposed using the tags that were auto-discovered. Then we have auto re-enrollment. If the machine changed its tags, that means that if someone came and changed the GPU in the machine, then you don't want to run a job thinking that it's, let's say, a Navi 10, but actually you just replace the GPU with a Navi 21, and then your results are going to be all screwed. So you want to detect this and just say, nah, abort, abort. Yeah. Also for configuration, we want to do as much of it automatically. So the serial ports that are connected between the test machine and the gateway, we want to detect automatically which one is which. So you can tell USB TTY USB 0 is actually mapped to the machine that has the MAC address, blah, blah. And we do this using a component named Salad, which could have been another thing that I could have put here, but didn't find a very beautiful image for this. And finally, we have self-tests that are displayed on the screen of the gateway that just tell you, like, do you have an IP? It checks for heartbeats of things, or do you are the two network interfaces working? We're going to get into this later. So there are things like this. But what can't we automate? Well, so far, the only thing we haven't automated is figuring out how, the mapping between the MAC address of the machine you want to boot and how to turn it on. So we're going to get into the power side right after. So this part is not automated and needs a little bit of manual intervention. Then network security, that's another aspect. So you don't want your farm to be used for instance, mining Bitcoins, as was just explained, or I don't know, be part of a botnet, be doing anything that would be damaging. You want your machine to be serving the people you care about and no one else. So since you probably want to make your machine publicly available so every project in GitLab could access it, then you need to be careful not to allow the machine to do things that you don't want to do. So the first thing is you want to put your CI infrastructure in a separate network from your office and home. That's rule number one. You don't want your farm to be able to spy on what you're doing. Then you should use a VPN to connect to the farm's gateway. Of course, WireGuard nowadays is so simple to set up, and it's great. Just do it. Then you need to block any port or protocol that you don't want to ever access, and this needs to be done at the router's level. So that could be, in my case, it's going to be just HTTP and HTTPS. That's the only two things that I accept going out because, well, we don't have other requirements. And then in the gateway, then we can be a bit more specific about which domain names we want to have. So for instance, accept anything going to free desktop. That's a good start. The distro repos or the repos for the distros of that you use in containers. So you can do, you know, like apt-get update, something like this. Could be also Docker Hub or Quay. Then you also want to have two network adapters for your gateway. So basically you create two networks. One that is so-called public network that you connect to the PDU. And this one, so the PDU is the power delivery unit. We're going to talk about this. It's to turn on machines and also connected to the internet. And then you've got a private network, which is connected to your test machines. And the test machines do not have access to internet, period. So that simplifies a lot of things. Only the runners have access. By runners, I mean the GitLab runners have access to the internet, and they can call the executor to start a job in the test machines. Okay. Then power cutting. Why do we need power cutting? Well, because it works around hardware state that just gets stuck until you you do a cold boot. I mean, I don't know how many of you experience this, that you can reboot the machine and something is just buggy until you turn it off, you unplug it, you plug it again, and then, oh, it works. Well, so yeah, have you tried turning it on and off again? That this joke is still just true. So why waste time debugging when you can just do that every single time? And if you use the power cutting as a signal to say just boot up, then you basically have a way to turn on machines as you want. And usually it's as simple as just selecting something like boot on AC or something like this. So most motherboards allow this. But if they don't, then I have a blog post on X.Org that is explaining how you can use a microcontroller to do it for you. So how do you do the power cutting? Then the normal way is to use a so-called PDU, a switchable power delivery unit. So you have a LAN port where you can control, where you can say, I want to turn on this port. That's pretty efficient. It's industrial grade. That means that there are some ratings on how often you can turn on enough machines. And it's controllable using SNMP. I put it as a pro, but it's terrible. But it's not as bad as going through a telnet session and literally saying menu 1, menu 2, menu 3, port 3, turn on. That's how a lot of PDUs can work. So you don't want that. SNMP is important. The con is that it's expensive. It can be like $500 new. You can find them for 200 or something like this on eBay, sometimes cheaper, but roughly $200. Another solution is IKEA. So you can do power cutting by just using these smart switches. I mean, they are safe, but then you don't necessarily know how often you can turn on enough machines. So that's a good question. One could assume that it's going to be, well, probably the same as relay. So I don't know, 50,000 cycles or something like this. So you definitely will need to replace these at some point. And they're relatively cheap. It's 35 euros for the gateway, 15 per socket later. So that means like every machine you would just pay $15. That's pretty good. You can find them everywhere because IKEA is probably everywhere. And the protocol is documented, and there are some projects, Python projects. Then adding new socket is annoying. I don't know if you've interacted with these. You need to bring these sort of switches there. It's really a pain. It's wireless, so it can be a pro or a con. But you can ask what is the state, so I guess it's fine. Like if there are some interferences, you can just keep on trying. And then there's another one, which is so-called Shelly plugs, which also have a power that can also report power. It has a REST and MQTT interface. They're relatively cheap. It's Wi-Fi based. And I put an example here of the REST interface. That's basically what you need. And finally, you need to have a UPS. So you want to make sure that if there is a surge in your electricity or microcuts, that the battery is going to take over and you're not going to fry everything and your machine is going to stay on. However, the difficulty is you need to make sure that the power rating is good for your farm. So you need to think about what is the maximum power consumption you're going to have in your farm, and you need to select these accordingly. And you want this for all your networking equipment and test machines, because what's the point of keeping your machine online if your router is going to go down and basically lose the connection anyway? So you need multiple ones. I don't think I have time to show this, but basically that's just a short graph of how things are connected. But we're going to see physically how things are looking. What the heck is going on? Mm-hmm. Okay, how does it look in practice? Good. So this is where my farm is. So there is the gateway, a couple of test machines here. It's just 3 for now. I have a PDU right there. I have a screen with KVM that allows me to look at the gateway and some other machines. There's ventilation, so it doesn't get hot there. So it's extraction. It's just lucky that it was there. I have some storage right now there, but it's going to be at some point hopefully full of machines. And I have a UPS and some networking equipment here. And you can see that the cables here have a different color because orange is the public network and blue is the private one. So it's easier to know what is going on. Then in the basement, even more in the basement, you can see basically that I have, so this switch is the one connected to my router, not my router, my modem. And then it goes into my home switch or home router. And this one is connected to everything, every appliance in my home. And then this one basically is also connected to the CI farm. So we have two at home. We have two routers. The one for the home and the one for the CI system. So with NAT, basically nothing comes in unless I explicitly enabled it. And then we've got a UPS to make sure that this would not go down in case of a microcut. And finally, it's loading. It's not the most important image though, so okay, it's here. That's just the modem with the optic fiber. So I'm lucky enough to have the fiber to the home, and I have 4 public IPs, 5 public IPs. So basically, I literally have a different IP for the CI network or home. So that's how it looks at home. So what about the promised 1,000 euro? Well, let's have a quick look at the bill of material. Assuming that you have the test machines and a machine that can be used as a gateway, then here is what you'll need: a UPS or more maybe, but yeah. Then a switch for the USB, so you can connect all the USB serial consoles, router, network switch, and this would be like 24 ports, so you can go for quite a bit. Big drive to store anything, and the old machine is of course free. We are thinking about making it possible to just have a Raspberry Pi, so that would be very cheap, or any of the single board computer would work. And then you've got a per machine cost that is quite minimal. For instance, here I was saying let's use the Shelly plug. So that's $30. That's the most expensive one. Then the USB to RS-232 adapter for the serial console, I put 20 euros because sometimes you need 2 if you need USB to USB. And I have just RS-232 in the middle with, oh yeah, I forgot the no modem cable. But anyway, 20 euros is fine, especially if you get them from eBay. Then Ethernet cable, some storage. This would be just 200 gigs, but that's sufficient for most applications. And then you're done. So that leads to about 1,000 euros. That's it. Any questions? I think I have 5 minutes left for the questions.
We do indeed. Well, actually, no, we don't, but okay, we can go with one. It will be fine. Imagine Simon Sir asks, what's the status for the software which ties everything together? Is it ready to use yet?
Almost. It's so it is public. It's in gitlab.freelstop.org/muproof/valvinfra. I say almost because we are changing the way we deploy things, and there are some services that we want to get rid of. And basically, let's say it's not ABI stable yet, but we are hoping to get there very soon. But definitely do come in touch if you want to experiment with that, and especially if you need help with selecting the hardware that you want to use for deployment.
Okay, and it looks like we don't have many questions aside from one quick addition. Why is MooPoof written on your UPS?
MooPoof written in my UPS?
On your UPS.
I don't see it.
Oh no, because this is from Jitsi anyway. Because your name shows up exactly as it would be on this device. Sorry.
Okay.
Okay, never mind. Just confusion.
Okay.
Okay. So
Very
that's
good.
all. That's all the questions we had from IRC. So please stay around for any questions should someone have more. And then thank you and have a great day.
Thank you.
And now it's time for the next talk of the day, a new CPU performance scaling proposal for tuning VK3DD and Proton by Ray Huang. Please take it away.
Hello everyone, how are you? Long time no see. I am Ray from AMD Linux team, and it's my pleasure to talk about the new AMD CPU performance scaling proposal in this conference. And we designed the solution at the beginning of this year and start upstream at this month in Linux kernel. The current implementation is verified on one of Zen 3 processors. Its name is Zen, and we will continue to enable more AMD Zen-based CPU series in following days. Okay, move to the background. And we were working with the Wolf software engineers to enable the Steam Deck on the AMD platform early this year. While we were tuning the Steam game's performance of Vulkan to D3D Proton, they found two issues on the AMD processors. One is something wrong with the CPU frequency prints, and another is a slow motion on the horizon zero jaw. And we spent a long time to investigate them and found quite a few problems for ACPI CPU freak driver on AMD processors. So ACPI CPU freak driver may not be very performance and power efficiency on modern AMD platforms. Okay, let's talk about the existing kernel frequency control here. Linux kernel provides a CPU freak framework to use kernel governors, and such as on-demand and schedule till policy to control the CPU clocks. And many years ago, Intel implemented ACPI-based CPU freak driver, and it is absolutely a great driver to provide a general solution on the legacy Intel processor before Sandy Bridge. Then they switched to the Intel-specific P-state driver in recently CPU series. However, current AMD CPU platforms are still using the ACPI-based CPU freak driver to measure the CPU frequency and the clocks, with switching only in 3 P-states. The ACPI-based CPU freak driver develops on the Intel platforms and will bring some potential issues on AMD processors as well. AMD hardware also provides the firmware-based CPU clock dynamic power measurement. It is also to control the processor frequency. So we call it as DPM. The ACPI CPU freak driver is not aware of AMD CPU clock DPM in the firmware, so we would have some conflicts to impact the final target frequency. So we plan to design and implement a new AMD CPU freak control proposal. This proposal is expected to handle the hardware functionalities such as AMD CPU SMU firmware and ACPI CPPC handling. The AMD processor provides MSR registers as the backend mailbox for the frequency control. Because MSR is a low latency register model that is faster than ACPI ML code interpreter buffer. So we implement a new AMD state driver instead of ACPI CPU freak driver for AMD platforms. It is able to use a finer grain CPPC frequency range instead of traditional ACPI 3P state to control CPU clocks. We can use even leverage kernel governors such as the schedule tool to predict the workload to calculate more reasonable design performance goals with the Linux CPU CFS scheduler. We mainly use the schedule tool governor to optimize the solution and manage the hints to the SMUC clock DPM to calculate the final target frequency. And these four performance values are defined for MDP state performance capabilities. They are the performance scales which are mapped at different processor frequencies. You know the different processor types have different frequencies. And the MDP state solution introduce a continuously performance scale between the highest perf and the lowest perf. The highest perf is similar with both the day before, and the nominal perf is similar with the P0 state. The processor frequency can dynamic adjust it during this range. These four performance values are defined for MDP state performance control. The performance scales, which are mapped at different processor frequency as well. User can assign the performance range as the hint to the hardware. The hardware can control the real-time frequency according to the hints that MDP state driver provides. And the fourth scale is difference. It provides hints if the driver wants to balance toward performance and energy efficiency. This entry is not implemented so far, so we will take care of this in the future. This kernel has several governors such as on-demand performance, power save, user space, and the schedule tool to control the general frequency exchange for most of CPU processors. Performance and power save set the highest and the lowest performance goals statically for the processor core support. The on-demand governor is mainly used for most of current processors besides modern AMD modern AMD Zen series CPUs. This governor sets CPU frequency depends on the current system workloading. And schedule 2 expect to the better integration with the Linux kernel scheduler. Load estimations is achieved through the schedule tools, schedulers, the per entity loading tracking method, which also provides the information about recently workloading. Okay, this is the big picture for the AMD CPU freak driver. And the the MD CPU freak driver is create a new kernel module named is MDP state and the Linux CPU freak subsystem. This module can access the CPPC relative MSR registers, and which provided on some of Zen 3 and later AMD processors, which includes the CPPC functionalities. The SMU former can detect the hints that MDP state passes while the MSR register and the response request into the hardware control. They will control the CPU clocks according to the performance goals from the MDP state module. The CPU freaks core estimates the CPU usage statics over the last period, which is similar with the SMU former to monitor the C0 resistance. Then they decide that the frequency is increased or decreased. However, this kind of CPU statics are mainly controlled by the ACPI processor idle driver in Linux kernel, and that is using the M-weight style translation to set CPU from C0 to C1. And current Linux kernel is mainly use the completed file scheduler to manage the processor scheduling. And the Linux CFS scheduler provides per entity loading tracking method to manage the real workloading at real time. The schedule tool works based on the DVFS for the task managed by the CFS scheduler. The DVFS is dynamic voltage and frequency scaling. And the real-time and deadline scheduler tasks are always running at the highest frequency. And it is the user mode CPU power extension tool to manage the CPU freak subsystem running status. We can also add MDP state support at this tool. Okay, the Linux CPU freak core offers a standardized interface for CPU freak subsystem. This module is to manage the CPU frequency and the performance while the MDP state API with the multiple MD kernel governors. We use the two identifiers to know whether the processor supports MDP state module or not. The module registers MDP state driver instance to implement the general operations in the callback functions, and it can execute the relative performance scheduling control that is dedicated for MDP state interfaces on the MD processors such as the adjust perf, target, and the fast switch. They are used for mapping the functions in the governor like the on-demand and schedule tool. Then the kernel governors can manage the P-state performance hints, while the MDP state module for each processor core. And we will implement MDP state CPU performance scheduling driver RST documentation to introduce driver details. And sorry. Okay, continue looking at the MDP state driver. The MDP state driver implements the CPU data to store the private MD specific information and function callbacks. We implement MDP state register read and write helpers for the capability and the request interfaces. This driver implement freak course request interface instance for the freak constraints. The constraint structure sets the limited range between the maximal and the minimal frequency between which register into the Linux power management quality of service framework. In future, we plan to implement kernel parameters to switch different frequency management policies and customize the different the policies to specific product and implement the support of EPP, energy performance, pre-reference control, and the prefer core. The prefer core is for single thread performance. Okay, there are two static trace events can be used for MDP state diagnostics, and one of them is the CPU frequency trace event generally used by the CPU freak, and another is MDP state perf event, a trace event specific to MDP state driver. It can monitor all the performance goals with MDP state programs to the hardware at runtime. The MDP state exposes several global attributes in the sysfs to control its functionalities at the performance level. The attribute files are located under the CPU freak subsystems to affect all CPU cores. They can indicate the highest, nominal, and the lowest performance and frequencies. And CPU power tool is the library user space tool to query the sets of CPU freak APIs. This tool is suggested by Linux community and widely used by Linux World for processor power configuration applications. And we will add two components such as MDP state performance frequency level and MDP state sysfs operation handling. Then user can control the CPU power tool to manage the MDP state module. Okay, we pick up the MDCzen processor to do some performance per watt testing on multiple CPU benchmarks. This is T-bench. And with the 128 clients result, their average data and MDP state got 3% improvement with scheduled till governor and a 10% improvement with the on-demand governor. And this is the git source benchmark test. It is also the average data, and MDP state got 19 improvement with the scheduled till and 26% improvement with the on-demand. And this is speedometer JavaScript benchmark for Chrome, and the scheduled till result is almost the same, and you can see 1/4% should be in the management error range. So they are the average data, and the MDP state got the 10% improvement with the 10% improvement with the on-demand governor. And this is the Horizon Zero Draw games under the same performance. And look at pictures. This is the MDP state clocks. You will see it's much lower than the ACPI CPU clocks. We can save more CPU power consumption here. Okay, finally, according to the test result on each benchmarks, we got very positive improvement with the new MDP state driver. We are in progress to upstream the whole solutions in the official Linux kernel. You can refer below repo to get the latest source codes of MDP state driver. The MDP state MSR-based APIs are the first time for the Linux solution, so we might face some potential stability issues. I need to do more testing and verifications. So finally, we hope this solution can be accepted by Linux community. Okay, that's all. Thank you very much.
Okay, and now it's time for the QA session. So the first question we have from Bas Nieuwenhuizen. Given that perf per watt is typically better on lower clocks, is the absolute performance still good?
We already do some testing confirm which compare with the performance and the dedicated performance and the dedicated for power, and even we can promise the performance is still is at least still the same, but we can by under the same performance we can save more power during for this least fine-grained performance range. And then Lexid a CPIP state driver.
And Michel Denset asks, what's the oldest version of Zen that can work with the new AMD P-State driver?
Yeah. So far for for this feature we still need the support from hardware and the system BIOS and PM firmware. So if the system BIOS and firmware can support this function, we can enable more legacy Zen based CPU series. But in fact we we are actually in progress to enable them in following days.
Okay, it looks like that's all the questions we have for today, so please hop on to the IRC channel in case someone comes along more. Thank you for your talk and have a great day.
Okay, thank you.
And now it's time for the next talk of the day, Video Decoding in Vulkan, a brief overview of the VK-KHR video queue and video decode APIs by Victor Jacques-Lial from Igalia. Victor, please take it away.
Hi. Welcome and thanks for attending this talk about the provisional Vulkan extension for video encoding and decoding. My name is Victor Jaques, I'm from Mexico, and I do multimedia programming for an employee-owned company called Igalia. We mostly do web browsers internals. Most of my work is with GStreamer, a multimedia framework for creating streaming media applications, as browsers are. In the GStreamer community, I maintain some models, such as GStreamer API, which is planned to be deprecated in the future in favor of a new one. All in all, I am not a graphic developer, meaning I am not actively working on Mesa, kernel, or Wayland, but I do have colleagues that are working on them. The graphics team. One day, they approached me and they told me that they became aware of a new extension in Vulkan for video decoding and encoding, and it looked similar to VAPI, which surprised me. I barely know OpenGL fundamentals, and I was hoping to dodge Vulkan for a couple years more. But they added, "We want to know if what you have been doing all this time with GStreamer and VAPI can be done with these extensions." And I said, "What?" One of the consequences of that conversation are these slides. The purpose of this talk is to give an overview of the concept used by the Vulkan video extension. I learned these concepts by hacking a new element in GStreamer Vulkan, a H.264 video decoder. The extension supports, at this day, H.264 and H.265 encoding and decoding, but I can only talk about H.264 decoding because that's what I did. Why do I want to talk about in the XDC? Well, because I wonder if these extensions might have, in time, a Mesa Vulkan implementations, perhaps as a Gallium front end, such as currently OpenMex, BAPI, BDPAW, etc. I like to assume that everybody here knows what Vulkan is. Just to be sure that we are on the same page, just I say that Vulkan is a cross-platform API under the Kronos Group umbrella, aiming for a huge number of tasks in graphic development. It is described as a common specification which boils down into a set of C header files, and its functionality is implemented by different drivers. Those drivers are provided by GPU vendors or, thankfully, by Mesa. So later on, I registered an account in Kronos, and as Igalia is a contributor member, the account was set up fairly quickly. And I got access to the Vulkan Video Technical Specification Group, or TSG. I knew then that the Vulkan Video TSG was proposed in May of 2018 to integrate hardware-accelerated video compression and decompression into the Vulkan API. On April of this year, the TSG published an introduction to the specification as is right now. If you're interested, please be sure to read the post. It goes into way more details than this book. Now a big disclaimer. The Vulkan video extension is provisional and is still expected to change. Driver, code, the specification are very new. They are not production ready. And as in the first maps in history, we ought to add the caption, "Here are dragons." Let's talk about video decoders. Nowadays, there are two approaches to video decoders, stateful and stateless. Stateful decoders basically work as black boxes. You get a bit stream and push it into the decoder. Eventually, you will get a renderable frame or an error. FFmpeg API is like that. OpenMax was like that. Kernels before API is like that, etc. Those are black boxes which internally keep the state of every single stream being decoded. Stateless decoders, on the other hand, expect to receive the stream state on every single frame to decode. They don't keep the state. Video stream state consists on the picture reference, because the frame may depend on future and past frames, also known as the decode picture buffer, DPB, the picture parameters, and the picture segments, or slices, or tiles, or whatever they've been called in the specific codec. The application then is expected to split the stream in byte stream pictures, to parse frames parameters and its slices, to keep the DPB, and if everything looks fine, submit all that information into the decoder and wait for an output image frame. Examples of stateless video processing APIs are, of course, BAPI, the new B4L2 stateless in kernel, D3D11 in Windows for Microsoft, Direct Show, and of course, bootcamp video extensions. Stateless decoders are gaining popularity because when using hardware acceleration, they require less chips, smaller blobs, and overall, they are less complex and they scale better. But they pass all the parsing burden to the applications or frameworks. Talking about frameworks. GStreamer is one of them for streaming media applications, as we already said. Its fundamental concept is pipeline, which is a set of linked elements that either produce, filter, or render signals. Those signals are discretized in buffers, and each element converts those signal segments into another type of signal, which will be consumed by the next element in the pipeline. A set of elements can be packaged in plugins. Also, there are base classes and helpers for a wide range of multimedia processes. So my task was to implement a GStreamer element which will process H.264 streams using the Vulkan video extension. Although GStreamer is more than 20 years old, until recently it merged the plugins and base classes required for this video decoder. To say, the GStreamer Vulkan plugin and the base classes for stateless decoders. GStreamer Vulkan is a plugin that uses Vulkan API to, among other use cases, upload CPU memory images into Vulkan images, renders them into the screen, do color conversion, etc. Besides, it offers a set of base classes for many Vulkan API concepts, such as devices, queues, semaphore, fences, etc. On the other hand, GStreamer Codec State Handler is a new library with base classes for elements that parse and hold the codec state for several different video codecs such as HEVC, BP9, AV1, etc. Then, the new Vulkan element is a descendant of the GST-H264 decoder base class. What is required in the Vulkan side? 1. The provisional specification with extensions, and 2. A driver implementing the version of the specification. Right now, only NVIDIA beta driver does all that. If you have a recent NVIDIA video card, you may try it. Also, NVIDIA offers a repository with a video decoding example written in C++. Once compiled, it provides a command line application which decodes and renders H.264 and H.265 streams. Though, sadly, it is linked with a binary-only library which does the parsing. Still, it's a good reference. And here's the URL of my Vulkan H.264 decoder merge request in the GStreamer GitLab. It is still a work in progress, but already Matthew Waters, the author of GStreamer Vulkan, already did an initial code review. The first item in the to-do list is the Vulkan color conversion from MV12 format to a single descriptor, with a single descriptor to RGB, suitable for rendering. That's the reason, sorry, why I cannot demo a rendering pipeline right now. The Vulkan Video TSG have the following design goals for the API. Programmers can allocate the exact hardware resources according to the properties of the stream to process. It can be used from embedded devices up to servers. It can scale up the number of simultaneous processed streams by just adding CPUs and video devices, GPUs, VPUs, whatever. It is style integrated with the rest of the Vulkan API, so it will be possible to do pre or post-processing of video images in Vulkan graphics pipelines as textures or so. The Vulkan video extension consists on 3-layer APIs. The root extension in red is Vulkan Chronos Video Queue, which provides the common API for either encoding and decoding. The next layer in yellow are composed by decode queue and encode queue extensions. The last layer, not in the diagram, sorry, are codec-specific APIs. Mostly they are C structures representing the picture parameters and metadata for the specific codec. When writing a video decoding application, the common initial steps are the following. First, to find a Vulkan physical device with the video queue extension and the video decode queue extension. If there aren't any, the application should halt. With the found device, the application must look for a queue with a family type of video decode bit and the H.264 codec operation. If they are not, the application should halt because it cannot process that codec. If available, we have to instantiate that queue. Third, query the device capabilities and verify if the requested stream fits with those capabilities. If they don't, if the stream is bigger, the application should halt. Later on, we have to instantiate the video session, which is an object associated with a single process stream. It specifies the codec profile. For example, in X.264 can be main, constraint, baseline, high, etc. The maximum frame size, the DPV length, output color format, input chroma, input luma, and so on. After creating a video session instance, and before the object can be used for any decode and encode operations, the application must allocate and bind device memory resources to the video session object. The required memory resources can be fetched by just querying the created video session. Then we have to instantiate a video session parameters, which is an object associated with a segment of current processed stream. A video stream can consist in several segments with different parameters. In the case of H.264 decoding, a segment at least contains a sequence parameter set, SPS, and a picture parameter set, PPS. A stream may use one of each or multiple sets in different segments of the stream. And you can add later on video session parameters as required by the stream, or delete and create a new one. After instantiating these objects, now you can call the command decode video, which is the only AP call in the video decode queue extension. It submits this command. It submits into the Vulkan command buffer the picture data to the code, such as bitstream slices, references, and output image memory. But the command decode video should be guarded by a pair of command buffer submission calls, which are command begin video coding and command end video coding. These API calls are common to decoding and encoding, and they are defined in the video queue extension. Command begin video coding receives as parameters, among other definitions, the video session object and the video session parameter object. And finally, the command buffer queue will receive a sequence of commands. Queue a command to wait for semaphore, to queue a command to begin video coding, queue a command to video encode, command to end video coding, command to wait for semaphore signal, and so on, until we demand a decoded frame to be rendered or used as a reference. For that, a fancy submit, and we wait for it. In the GStreamer element, Vulkan H.264 decoder, each frame is fenced, so that's a future optimization task. And that's it for my side. Thank you very much for your time, and if you have any questions, I will gladly try to reply them. Thanks.
Okay, and we're ready for some questions from IRC. Let's wait for a bit until first questions come in. Simon Serre asks, any plans to implement it in MISA from any vendor?
Hello, guess you can hear me all. As far as I know, there are not. Even though in the TSG, in the technical specification groups, there are vendors from different GPUs manufacturers, but I don't see anyone from MISA participating early. But the idea of this talk is to open that idea into the mess.
Okay, let's wait for a bit more questions then. Okay, it looks like there won't be any questions for now, so please hop onto the IRC in case someone asks some more, and then thank you very much for your great talk. Have a great day.
Thank you. Thank you. Bye.
And now we're ready for the final long talk of the day, State of the X.Org by Liut Paul. Liut, Paul, the stage is yours.
Hi, I'm Lead Paul. It's nice to see everyone here, or well, rather, it would be nice to see everyone here if you're in physical location. I'm secretary of the X.Org Foundation, and this is our presentation detailing the state of X.Org this year. So first, I'd like to give a very special thanks to Intel and all of our conference organizers who helped run this. It's been a lot of hard work, and we wouldn't have been able to do this without them. So thank you all for being such a huge help in running this conference. So sponsors. We had about 10 sponsors this year. Unfortunately, we didn't have any travel grants, and this was mostly due to COVID-19. Well, since we don't actually have a physical location. And of course, thanks to Manassi for doing all the invoicing for all of our sponsors. Great work there. And of course, thank you, Daniel Vetter, for doing all of the sponsor hunting. Super appreciated. So this year we got about 35 talks compared to 33 from last year. Actually, that's wrong. It should be technically 36 talks since we got one lightning talk just today. So we had 21 full slot talks, 7 half slot talks, 5 lightning talks, and 3 workshops. So big thanks to Samuel and the rest of the papers committee for reviewing all of the presentations. Had a lot of cool stuff going on this year, and hope to see a bunch of cool stuff going on next year as well. So XDC 2022 RFP process. This is also a little bit out of date because we already had a proposal actually that was approved. But if you are still interested in trying to send an RFP, feel free. So sponsors welcome, of course. And I've got a link to the sponsorship levels right there and how to get involved. We're still not sure if it is going to be virtual, unfortunately. We would like to hope it's going to be physical, and I think that's likely, but of course it's all going to turn out on how things end up being when the time comes around. So new things. One of the things that we're currently working on is plans to allow driver maintainer access to non-redistributable game traces for usage in testing and debugging. Also, I'll have to check that message after. Oh, yes. Okay, yes, I did mention the lightning talk button. Anyway, so plans for allowing core driver maintainers to access non-redistributable game traces for usage in testing and debugging. We're pretty excited about this because one of the big things with game tracing in general is that we don't necessarily have the ability to redistribute the games that are involved. And our hope with this is that we would be able to have a select group of like core maintainers for various drivers that would be interested, who would be able to get access to traces from these non-redistributable games for legal means and be able to actually use them in order to help triage various regressions or bugs or that sort of thing that may be very difficult to reproduce otherwise. This, of course, means more stability for games overall, and it's pretty exciting. Okay, so X.org/freedesktop.org infrastructure updates. I won't go over too much here since Ben already had a full presentation on it. But to re-emphasize, we really need volunteers. Bentis has done a great amount of work so far, but it's definitely a lot of work actually keeping the CI maintained, and we can use as much help as we get. It's a volunteer position, and anyone is welcome to apply. And it'd be a huge help if anyone interested could. So, of course, we're making good progress financially on that subject. We're down from $6,000 a month down to about $800 a month down for costs. which is absolutely fantastic. And the end goal is to get our hosting costs to $0 a month. Hooray. We've still got some issues with the cluster being flaky from time to time, but it's working pretty well overall. And of course, again, we do need volunteers. And of course, a huge thanks to Equinix Metal for hosting our servers for free. None of this would have been possible without their help. So freedesktop.org Code of Conduct Transparency Report. So we had a lot more reports than previous years. Most of them were on GitLab, and I think the reason for this is actually mostly because moderation on GitLab can only really be handled by people with admin access. So I think a lot of this is less a change in actual behavior in the community and more so just now things have to be handled slightly differently with Code of Conduct. So we see a lot more reports going through GitLab, whereas before they likely would have just been handled on the maintainers end of things. And it's also worth noting a decent amount of those reports were also just spam bots. So like, just people creating accounts to post spam links, that sort of thing, not any actual conduct violations. So excluding the spam bots, we had 2 complaints of recurrent behavior that resulted in bans, and we had 4 formal complaints resolved with warnings. So Google Summer of Code, endless vacation of code, and outreachy. So unfortunately, one of the problems we ran into is the Google Summer of Code changes to the timeline don't allow for anywhere near as much time for working on projects as we used to have. And this pretty much means it's a lot more difficult for us to actually come up with project ideas for students. We're still open to project ideas if anyone has any, but yeah, that's mainly the main reason why we haven't been able to be involved this year. Additionally, though, we need volunteers to actually help keep these projects running. Currently, our administrator from a while ago stepped down. Thanks for all of the great work, Trevor, by the way. They helped run these programs for a number of years and super appreciated. But now we need a new volunteer. And we are currently looking for an admin to coordinate X.Org's involvement with Google Summer of Code, EVOC, Outreachy, etc. And that's really the biggest thing right now. We also need to get project members who are willing to be student mentors. People stepping up to do that would be super appreciated. And of course, like I mentioned before, project ideas. Of course, I've included a link to a mailing post that you can find that has more information on this. And I will be uploading the presentation after the talk. So, of course, I've included a photo of my cat, Serena. I've done this to get everyone's attention to this slide because she's adorable and, why not? So Foundation, if you are not already a member of the Foundation, please feel free to sign up. It's super encouraged and you get the ability to request phases specification access. Cool. And if you want to do Kronos conformance submissions for your own drivers, you also need to be a member of X.Org, and we can handle working with Kronos and getting all the things in place for that. And just to emphasize, anyone involved with X.Org or freedesktop.org projects at any point is qualified to be a member. And of course, we've got the links there, members.x.org. So XDC, where will it be hosted? I'm not telling you that. That's a secret. I'm never going to tell. But our next presenter may tell you where it is. So if you want my advice, you should probably stay tuned. All right. And it's a pretty short presentation, so I'm done a bit early. So do we have any Q&A?
Okay, do we have any Q&A? That's a good question. Let me ask on IRC. Okay, it looks like there are no questions at the moment, so we might just have to move over to IRC for any future questions. And then thank you very much for the update on the X.Org, and have a great day.
No problem. Have a good one, everyone.
And we're ready with the last block of the conference, which is lightning talks. We'll start with the first lightning talk by Jeremy White, spoilers from XDC 2022. Jeremy, the stage is yours.
Great, thank you. So I want to ask, do you guys remember when you could see people face to face? You could shake someone's hand. You could look someone in the eye when you told them just how bad their code was. Well, we're hoping that we get to do that all again a year from now. And obviously, we don't know what's going to happen between now and then, but we have made plans to be able to get together in person. And so myself, my company Codeweavers, and the Wine Project would like to invite you, the X development community, to join with us in a technical conference. So we, the Wine Project, have long admired the X development community. We depend on your work. We curse you under our breath, and we want to party with you in Minneapolis, Minnesota, the City of Lakes. It's part of the Twin Cities of St. Paul and Minneapolis, and in my completely unbiased opinion, the best place to work, live, and go to a technical conference in the world, particularly in the fall. We will be meeting at the St. Thomas Opus College of Business in their conference facility that is in the heart of downtown Minneapolis with lots of restaurants and bars nearby. We'll all get to go on the world's largest private skyway and get hopelessly lost. It should be a great time. And I want to take a moment to point out the dates, which are October 4th, 5th, and 6th, 2022. I want to give credit to Eric Heiler, whose idea this was, so it's his instigation, and to James Ramey, who actually did all of the legwork putting this together. So I'm just taking credit for their work, which is what CEOs do. And there is a tiny little footnote. We are certainly very aware of COVID, and we are preparing for it. We're allocating extra space so we can pivot as need be, but we're really hoping that we can all be together and have a joyful time together in Minneapolis in a year. I hope to see you then.
Okay, the next talk of the day is going to be Jason Ekstrand and Bas Nieuwenhuizen, who's going to talk about conclusions from BVH building with RedV and Envy.
All right, if everybody can see my slide, I hope so.
Indeed.
So we had a talk this morning for a couple of hours about the BVH building stuff that we've got at Intel and whether or not we can reuse that for RadV. The end takeaway is good news. It looks like code sharing is going to be possible with some caveats. So one of the things that's unclear is exactly how command stream with control flow is going to work on AMD. Bas has some ideas about how that might work, but his ideas are currently untested, and the documentation there is not real great. So if any of the AMD people could throw him some real docs, that'd be appreciated. For some of the ALU stuff that we have to do, because there's some calculations that have to happen on the GPU. On Intel, it's done in the command stream with ALU. RadV might have to kick off a compute shader. Switching over to Node for compiling GRIL files is looking likely, but details are very TBD. And it looks like we're going to have to generalize some things a bit. So AMD does indeed have its own BVH format. This is not something that I knew going into the discussion. And one of the big differences is that their BVH is a 4-array tree instead of the 6-array tree on Intel. So we're going to have to generalize some of the algorithms so they can work on 6-array either size tree. We might have to generalize some of the scratch space calculations, etc. And clearly AMD is going to have a different BVH generation backend. But the code is already fairly well set up for that because Intel's BVH format is consumed directly by hardware, and we wanted to be able to change that in the future if we needed to. So it's already fairly well designed to be able to take different backends. So it looks like it's possible, but there's a lot of investigation that still needs to happen. The next big step is that somebody on my team needs to actually post what we have so that Bas can start playing with it, because until he has something concrete to work with, it's a little bit harder to come to actual conclusions. So I think that's basically where we left it. Bas, do you have anything to add?
I guess the other thing is like obviously we need to figure out the command streamer stuff like that can happen in parallel, and then hopefully that will, especially when the girl code is posted, that will give us a good way to get to move forward.
Okay, I think that's all we had. Short,
Okay.
sweet, to the point.
Thank you very much. Up next is Carl Herbst with Rust in Mesa.
Yes. I hope that works. Okay. I hope you can see it.
Yep.
Okay. Yeah, so I wanted to learn Rust a little bit, so I was trying to investigate how easy it would be to use it inside Mesa directly. So my main goals here was just to learn Rust. And I actually wanted to learn more about OpenCL specification, how that all works, because I was always, looking into Clover, and a lot of things were just, why does it look like that? And I wanted to actually understand by implementing OpenCL how that works out. Like, why was it done this way? So to actually use it inside Mesa, I had to figure out how to use Rust to implement a certain API, and I had to figure out how to, be able to call into already existing Mesa code. And another factor is like, because we are using Mason inside Mesa, and we can't just use cargo or something. I had also to investigate how well that works, and Dylan Baker was quite helpful with that and fixed a few issues or added support for bindgen to actually generate Rust bindings for stuff. So as I said, bindgen is a tool to generate bindings. So you have a C header file or a lot of them, so you can just generate Rust bindings for that, which includes constants and function definitions and all that kind of stuff. And that's essentially it. So besides that, I just had to write some Rust code. And I have a bunch where the code can be looked into if you really want to. It's a link in a PDF, so you don't have to copy it or something. Current status is I can actually do some OpenCL stuff with it already. So buffer, like reading from buffers, writing to them, copying them already works. There's no compiler integration yet, which is something I'm a little bit scared of because we have LLVM and then Near as well. And without I suspect this can be quite complicated, and there are also problems like static inline functions can't be used yet, and Near is using tons of those. So in order to use those, I actually have to, write a library which is just including the code and generate actual functions for that. So I have a object file with all those functions, which, with static inline functions you normally don't have. And I can't use external crates through Meson yet. So this is a little bit annoying because Rust is easier if you don't have to take, for example, mutable references. And there are a lot of container libraries which give you, for example, a queue or vector or array or something. You don't have to take a mutable reference to change them, like inserting elements or removing them. Yeah, that's it.
Okay, and the next talk today is going to be Demi Obenur with summary of discussions from the multi-tenancy workshop.
So the short answer for the multi-tenancy stuff is that it'd be nice if more people showed up. It turns out that there's a lot of uncertainty and a lot of implementing it the way I'd like to see it implemented is going to be a lot of work because it requires a lot of work. It requires, depending on how it's implemented, it could be as much as n times n for n devices and m OSs. Hopefully, I think it could be reduced to n plus m. But there's also, but still, having to create a whole different driver, a low-level driver, in order to make it minimal enough for hostile multi-tenant use is going to be quite tricky. And also there's the question of, does the hardware actually support this? Is the hardware robust, for instance, against instruction streams that try to bypass page tables to access memory that they should not be able to access? And that is really tricky, obviously, because I'm not a hardware expert, and so that brings the question of, and so that's still an open question. Also, actually writing this would require, I mean, obviously it's a lot of work, but I still think it'd be worthwhile if it could somehow be implemented, because the payoffs of secure multi-tenancy on commodity GPUs are enormous. Namely, basically not having to deal with regressions. Like, for instance, CubesOS currently it looks like it may be suffering from performance regressions because software rendering is being de-emphasized and reduced to fallback paths. And that's really annoying. And so hopefully if hostile multi-tenancy and commodity GPUs were possible, then it would be really, really nice if that could be done. And it's the libvf.io work might also be helpful if that gets to a point where it's usable on Zen or in a, for instance. And if its attack surface is sufficiently low, that generally means having the emulation outside of the hardware domain. But yeah, it's a hard problem. And I'd still like to get more information, to somehow get more information about whether it can be done, what it would be involved, and so on.
Okay, so do you have one more topic, or should we go to the next talk?
I guess the other, probably the main other. So basically, there's a lot of unresolved questions, and if there's some place that they could be discussed more long term, where there might be some like hardware people who know a lot about hardware who could answer some of them and so on, that'd be awesome.
Okay, thank you very much then. So up next is Matthew Herb with the X.Org Security Birds of a Feather summary.
Okay, so for this workshop, those are the topics that I had in mind. Mainly, we need more people to help handling with the X.Org security issues. This was a bit of a failure because at the workshop we were at a maximum of 5 people during the interactive session. I don't know how many people followed the session remotely using the CCC or YouTube, but this makes not many people really wanting to participate. But we will try to fix that by also sending an email for a call to participate to the developers mailing list. We spent some time talking about ongoing security issues, among other the X11 socket person in the middle issue that Demi reported 1.5 years ago, and for which we should really start to try to fix it and move forward, testing the patches that were submitted at that time. We also discussed about some general ways to improve X security by implementing the XCB on the X server side, or other ideas like also bringing some Rust in the code that may attract new people, because it's something that may be interesting and motivating for people who have not yet tried to study the X protocol. It may be a new way to attract more energy there. We also discussed a bit with Benjamin on the way that private issues on GitLab may be used or not to report issues. Currently, the situation until the discussion, the situation was a bit unclear to me. Now we have a bit more understanding, and we will probably create a separate project so that we can have private repositories for the projects to actually test some patches before the security advisories go out, and the new and the fixed modules are released. And finally, we also discussed a bit about the fact that we need more documentation. For instance, all the new stuff around Wayland, I'm not sure if it's correctly documented somewhere. What are the security contacts, and if someone would report a vulnerability in libweston or libwl routes to XOR security, maybe we would suffer a bit and struggle a bit to figure out who to forward this to. So we need to generally document the process a bit more. And this can also be useful for package maintainers who may get direct reports about security issues if they don't know how to move forward, how to allocate a CVE ID, how to do an advisory. We have some documentation existing. We just need to refresh it and make it more visible on the X.Org wiki or on a GitLab wiki. That's about it for what we discussed during this workshop. Thank you.
Okay, thank you very much. Up next is Martin Rucola with notes on the CI workshop.
Okay, so that's a quick summary from the workshop. So we had two main topics, trace-based testing and then kernel testing in CI. So let's start with the trace-based testing. So one of the important findings was that reviewing frames outputs was really hard. Just looking at a single frame, it's hard to notice if there are things missing like heads or something like this, or just general misrendering. Then the next thing was that the frame check, using checksums of frames works on some games on very simple outputs, but on modern games it's becoming well, impossible. Then so we were discussing about returning to reference frames and then having a way to overlay and say basically at this particular pixel we have seen that up to that much variance, and this way if we were to ship the reference frames along with the traces, then we could easily check if the frame that we just generated is valid or not. Then we're also investigating creating this reference frame for all the GPUs and GPU drivers. Rather than saying, hey, it's okay if this for this particular GPU only these pixels are going to change, but being more generic actually, and being for instance filtering if it is different on different GPUs, then it's acceptable, because from a user point of view, most pixels don't really matter. if you're off by 1 or 2 on every component. So so we'll try to make it somewhat general and just catch big changes. And to catch issues that would be a bit less well, easy to catch, especially in places that change a lot, then we're talking about potentially looking into temporal stability of the frames to avoid having something that might look good in one frame, but actually is flickering a lot between frames. And we could catch some issues like this. And so quickly, this is, for instance, a frame that renders the same on all our GPUs, and that's a frame that doesn't. And if we look at where the changes are between the two, between two images from the same with the same driver, then we see basically that anything around geometry is problematic. Although here it's not too much geometry, but you can see that there are changes there. Then, for the GitLab-based kernel testing, developers can start using GitLab for their kernel trees, but we cannot move yet DRM-tip and DRM-MESC because that's too high traffic and too, well, we need to ramp up slowly, basically. So let's start with smaller projects like Nuvo already started, and FreeDreno and some others can be added, and hopefully they're going to pave the way and figure out what works and what doesn't. Code submission is going to be difficult. It has to be somewhat of a hybrid model. We cannot have everyone sending merge requests on GitLab because, well, we cannot expect people outside of the community to connect to our GitLab instance and follow things there. So the proposal was to have the core contributors host the project on GitLab and use MRs to test their codes. Occasional contributors will send their patches through the mailing list as usual, and then because we want to make sure that people can, outsiders can review the changes, then we would set up GitLab to send notification to the mailing list of the project. We also decided that, well, I mean, this was already decided before, but basically storing the GitLab ci.yaml file can be done in upstream. Daniel Vetter and Dave Early were fine with this, so this is very good. That simplifies everything. And that is it.
Okay, and we have one more talk of the day, and that is going to actually probably be me. Okay, so how we did the X.Org conference 2021 today. So this is how my setup looks like, and looks almost professional, but basically it's not as much as you think. The third screen would be very useful for the mainstreaming setup. The microphone is mounted on Faith. It's not really mounted on anything. It's just like standing there in the shock mount. The second PC is absolutely required for monitoring the stream. And in terms of how everything is set up, this is roughly how we did it. We had two primary setups. One was my box on Arch here, and the backup box for Maciej Domotowski's home. Both of these machines were just using OBS Studio for everything. And then we had two machines set up on Hetzner. One was with the Jitsi instance, where everyone connected to. The second was the Nginx box with Nginx RTMP forwarding. And that was pretty cheap because it cost us like €5 in total for the 3 days of the conference. And that forwarded both streams to YouTube and media.ccc.de, which was absolutely amazing. Thank you very much for your support this year. It was wonderful. And in terms of how much actual resources those boxes were using, we had about 100% CPU usage on the GTC box during workshops, with about 40 people on those, and about 20% on the Nginx box. So we could make it even cheaper, but it was fine. Okay, so now the part everyone's waiting for, the fuck-ups. Surprisingly few though. So the primary streaming box had Arch installed, backup had Ubuntu, and font configure free type configurations was mismatched. So OBS scenes gets misaligned, and we needed to fix that really quickly before the conference started. The RTMP gateway had nginx with the RTMP module built from sources, and then Ubuntu decided to upgrade itself overnight, and that broke the setup about 10 minutes before we were supposed to go live, which was interesting. The backup setup was used for workshops, so I thought that we could just enable the Jitsi recording in case we had to switch over the backup to the main talk recording, but I tried the Jitsi recorder today, and it turns out it does not work. So we pretty much went without a backup for 2 days straight. Great fun. And we also had a pretty nice backup placeholder, but we did not get to use it even once. Aside from that, 2 small social issues. I forgot to lock YouTube comments on day 1, and that ended up just about as well as you think. We just had to swing the banhammer a little there. And then trying to keep up and just pay attention to everything that's happening on the stream with the speakers and everything is a bit too much for like 7 hours straight. There needs to be someone to swap out after a few hours. And aside from that, you get stressed, you make more mistakes, those mistakes cause you more stress, and then everything just devolves into slow panic. The first day was hopefully not too bad, as long as you did not see what was happening behind the scenes. It was fine though. Okay, so we did almost everything with free software. So free software, video editors, image editors, pretty much everything. The only exception was the NVIDIA encoder for the actual stream, because that's what I have in my box. If you want to check out the stream assets and the configuration and everything with it, it's on GitHub under this link. It will be updated with everything we made during the conference in 2 or 3 hours. And the videos are now being processed, so it will take a few days, but you can get either the live replays now or the pre-processed and nicely cut up videos in, a week or 2. Okay, thank you very much. Okay. And that's it for the lightning talks. And now it's time for the closing session by Radosław Schwichtenberg. And we're ready to go with the final session of the day, and that's the closing session by Radosław Schwichtenberg.
And we arrived to the end of this 3 days long journey. I really hope that you had fun, you met great people, learned something on the way, and as always, I keep saying, won't take you much time, but before we close, I'd like to spend some time sharing thank yous all over. So let's jump in. Sponsors. Without sponsors, the conference wouldn't be possible. So big thank you goes to our platinum sponsor. Intel, to all our gold sponsors. Thank you to Google, NVIDIA, ARM, Microsoft, and AMD. Thanks to our silver sponsors, Igalia, the Linux Foundation, Collabora, our bronze sponsors, GitLab, and Kronos Group. Thank you for supporting us this year, C3VOC, for providing us with great streaming service. First, I'd like, well, organizers. I mean, without them also it wouldn't be possible. So first I'd like to start with thanking the Intel Open Source Graphics Center that we proudly represent. Without our boss, Hillary, allowing us to be here, it wouldn't be possible. Second year in a row. So thanks a lot. Thanks to Richard and Maciej, super smooth experience. It's thanks to your hard work and your enthusiasm and all that's included there. And last but not least, Sam, thanks for all your support this year, but also last year. I think that XDC should actually become your middle name. Thanks a lot. It's always I'm always glad to work with people so enthusiastic and focus oriented on details and so on. Thanks, Sam, for your hard work as well. Our speakers, we had plenty this year, so thank you a lot for providing your talks. It's probably a third slide where I keep saying without you this wouldn't be possible. So we had really great talks this year, amazing talks. So thanks for your contributions. I hope that you will consider attending the XDC in future years and also providing some talks and maybe how some of the stories that started here this year or last year developed. Hopefully in person next year. Using this occasion, I'd like also to remind you to upload your slides to our websites. There is a couple of slots still without slides, so thank you a lot for attending. But upload your slides. And last, not least, everyone who participated. Again, without you, it wouldn't be possible. It's you for whom we are spending our efforts, our time, and for whom we created this experience. So thanks a lot for being with us this year again, and hope to see you next year. Thanks a lot.
you.